Okay, so I hope everyone is fine there, and today we will revise power electronics because it's an important subject, and this is the last subject. I suppose we have revised almost every subject, so today we'll cover power electronics. So don't forget to like this session, and if you have not subscribed our channel, so please subscribe the channel. Okay, so I think we should start now. So let's start the session, guys. Let's start the session. This is my introduction, and I teach actually entire electrical engineering, so almost every subject is covered. Now we are going to start power electronics. Okay, power electronics, in power electronics we will have two sessions. This is part 1, and tomorrow we'll have part 2. Okay, so let's start the session, guys. But before that, let me tell you, there is one master MSQ series is going to start on 17th of January, because in last year, if you look at the last 2 years. Tell me, guys, is it clear now? Wait, is it clear now? Okay, thank you. There was an internet glitch, and we may face this type of internet glitch in maybe 2 or 3 times in this session, because in every session I face the same problem. But anyway, let's start the session, guys. So there is one MSQ series which is going to start from 17th of January. You can attend this series. I was telling you that in last year, if you look at the ECE exam, ECE paper, in ECE there were 14 MSQs. So we are expecting that this year they will ask in electrical also. So do attend this session also. These sessions, there will be some 10-20 sessions on MSQs. So please watch these sessions. And let me tell you, guys, there is one open mega mock test for GATE 2023. So you can register for this test also. Registration link is given below in the description. You can find that link, and you can register for mega mock test. Okay, and there is one mega workshop is going on 15th of January, and it is for GATE 2024 student, and it will be taken by Abhinav Negi sir. So recommend your juniors, recommend your friends who are preparing for GATE 2024. Okay, one general aptitude session is also going to start, and it is coming soon, so date will be announced very soon, and this session will be taken by Rakesh Talreja sir. So I hope you will enjoy this session, and you can get easily 15 out of 15 in this session. Okay, and let me tell you, mathematics is again very important subject. Rakesh sir and Ankit Joshi sir will take this session, and again this session will be announced very soon, and you can attend this session for mathematics, because mathematics is very important subject. Now it's time for the test series, guys. So don't forget to join the test series, and this test series is provided by BYJU'S is also providing the test series, and you'll get many tests in this test series. Approximately 60 plus tests will be there, and the interface is exactly the same which you are going to see in the GATE exam. Okay, so let's start the session, guys. Those students who have not subscribed our channel, please subscribe this session and like this session and press the bell icon so that you get the notification. Okay, so let's start the session, guys. I think everybody has joined. So in the power electronics, first of all, let me tell you which topic I'm going to revise today and which topic I'm going to revise on tomorrow. Okay, so my target for today's session is the first topic which I'm going to revise is phase controlled rectifier. Phase controlled rectifier. Phase controlled rectifier. Okay, so today we'll revise that. Obviously, for revision of this topic, I will also revise the basics of power electronics, because basics is again very important. Otherwise, you can't understand the phase controlled rectifier. In tomorrow's session, I will revise DC-DC converter, DC-DC converter, DC-DC converter, and inverters. So we will cover this topic on tomorrow's session. Okay, So let's start with the phase control rectifier. To understand the phase control rectifier, what we need to understand is, first we have to understand the AC transient. So in AC transient, maximum student face difficulty. Why this is important? Why this AC transient is important? AC transient is important because sometime we need the current equation. You will understand why, maybe in the upcoming topics you will understand why I am teaching this AC transient. So you should be aware of the AC transient topic. Let me revise this topic and let's take a question after that. Okay, so let me revise this AC transient first. Remember, whenever you have AC supply, let's say you have this circuit R and you have one resistance and inductance. Okay, you have one resistance and inductance, and let's say here you have the switch and here you have the supply. The supply is Vm sin omega t. Okay, Vm sin omega t, and you have this resistance and inductance, and if you close the switch, I need to write this current equation IT. Now the problem is, many students think that, sir, we can write this current equation using the Laplace transform. Obviously you can use the Laplace transform, but the problem is, in Laplace transform it will be very lengthy. So we will go with the direct method. So direct method is, remember, this current will have two parts. One is steady state part and one is transient part. Now how to look at the steady state part? The steady state part is very simple. You have studied from network theory what is the steady state impedance of this. So the steady state impedance will be, let me calculate the steady state current. Steady state current will be the steady state voltage divided by the steady state impedance, and the steady state impedance is R plus j omega L. Okay, so this way you can calculate IT steady state. Steady state current you can easily calculate like this. Okay, now what this value will be? So this value will be, IT steady state will be equal to Vm by Z. Z is the magnitude of this impedance. Vm by Z sine of omega t minus theta Z. Okay, this will be my steady state current. This current will be steady state current. Okay, now Ashok is saying, sir, how to remember formula during preparation? No need to remember any formula, at least in power electronics. Okay, you don't need to remember any formula. I'll tell you why. Okay, so this is the steady state current, guys. Now if you want to plot this, this steady state current, this steady state current is a sine wave, but it is lagging by some angle theta Z. Theta Z is the impedance angle. Okay, so if you want to plot it, it will look like this. It will look like this. At t equal to 0, you can see that, or maybe at omega t equal to 0, the value is minus Vm by Z sine theta Z. Okay, this is the value at omega t equal to 0. Now the problem is, okay, and this point is theta Z. Now the problem is, we know that after closing the switch, there is an inductor. Na? The initial current in the inductor was 0. So the inductor will say that initial current has to be 0. To make this current 0, there will be one more current, that is transient current. Why we need to make this current 0? Because of inductor. Inductor is saying that my initial current was 0, so I have to start from 0 only. That's why to make this current 0, we have to introduce transient current. So there will be one transient current. Okay. Now what is the value of the transient current? The transient current will start at this value, and this value is Vm by Z sine theta Z. Whatever the negative value is, whatever this steady state current negative value is, opposite to that will be the transient current, and it will decay exponentially like this. Is it fine? So what will be the equation for IT transient? So IT transient will be equal to Vm by Z sine theta Z e to the power minus R by omega L omega t. It will decay exponentially. Okay, this way you can write the transient expression. It is actually t by tau. Time constant of this circuit is L by R. So e to the power minus t by tau, we have to write this initial value into e to the power minus t by tau. t by tau. So if you put the value of t, if you put the value of tau, it will become e to the power minus t divided by L, and this will be R. Is it fine? Now what you can do is you can divide with omega and multiply by omega. So this will be omega L, this will be R omega t that I have written here. Okay. So I hope you understood how to write the transient expression, how to write the transient current. So the total current will be this current plus this current. Okay. This way you can write the total current. So the total current IT will be equal to, so IT will be equal to IT steady state, which is Vm by Z sine of omega t minus theta Z, okay, plus the transient current Vm by Z sine theta Z e to the power minus R by omega L omega t. Okay, this will be my this will be the expression for the current IT. Okay, I hope it is clear to everyone. Now on this AC transient case, there will be many situations, like if the load has some RLE type of situation. Okay, let's say the load contain E also. Okay, let's take one more situation, and in that situation what I'm doing is I am taking R, L and E. Let's take the values itself. Okay, so let's take the value also. This is 10, this is 20 volt, and let's say 0.2 Henry. This is 0.2 Henry, and here we have the switch and the supply voltage. Okay, the supply voltage is better we take this as 0.1 Henry. Okay, let's take it 0.1 Henry so that it can become simple to calculate. Let's take it 0.1 Henry, and the supply voltage is 100 sine of omega t. Okay, omega is given as 10 radian per second. At t equal to 0, we are closing the switch. I need to calculate this current IT. What will be the expression for this current IT? Tell me guys, what will be the expression for this current IT? So we can calculate this current IT. How to calculate, guys? Tell me. Again, there are two sources now. So what we are going to do, we are going to first deactivate this source. We will calculate the current due to the AC source only, and then we will calculate the current due to the DC source only. Okay, because there are two sources. So we have to calculate the current due to AC source as well as the DC source. So can you tell me quickly what will be the expression for current IT? So first let's deactivate it. Don't look at this DC voltage source. So if you are not looking at the DC voltage source, if you are considering only the AC voltage source, then the current IT will be equal to, let me write it directly, IT will be equal to, we have deactivated this. So obviously it is sinusoidal steady state voltage divided by the steady state impedance. This will be the steady state current. What will be the steady state current, guys? Tell me. It will be 100 sine of omega t divided by R plus j omega L. R is 10 plus j omega. Omega is 10 itself. L is 0.1. Okay. So it will be 10. Omega L is 10 itself. Oh, not 10. Omega L is 1. So better you take H equal to 1. Wait a minute, guys. Because I want to make it simple. So let's take H as 1 Henry. Okay. Now it will be simple. Now you can see that what I have done is, this was the steady state voltage, 100 sine of omega t, divided by the steady state reactance. Steady state impedance. Steady state impedance is 10 plus j omega L. Omega is 10, L is 1. So it will be J10. Okay, this will be my steady state current. Now what is this value, guys? This value will be 100 by 10 root 2 sine of omega t minus 45 degree. Okay, this will be my steady state current. Now we have to add IT transient also. Now what is IT transient? Can you tell me, guys? What will be the IT transient? So what we need to do is, first you put omega t equal to 0, because we are closing the switch at t equal to 0. So we have to look at the steady state value at omega t equal to 0. At omega t equal to 0, this value came out to be negative, and it will be minus 5. You can see that sine of minus 45 will be there. Na? If you put omega t equal to 0, it will be sine of minus 45 degree, and sine of minus 45 degree is minus 1 by root 2. Okay, so you multiply this 100 by 10 root 2 with minus 1 by root 2, so it will become minus 5. So you have to take 5 here, e to the power minus r by omega L omega t. Okay, this will be the expression for the transient current. I hope it is clear to everyone. This is my transient current. So we have calculated the current due to, and also you can put the value of omega L and omega t. So if you are going to put this omega L, it will be 10 and r is also 10. So this will cancel. This will cancel. Omega is 10 itself. So the entire equation will be 10 by root 2 sine of omega t minus 45 degree plus 5 e to the power minus 10t. Okay, this will be the current equation for the due to the AC source. Okay, due to AC source we have calculated the current equation. Now what about the DC source? The DC source, if now we can deactivate this. If you have deactivate this, if you can deactivate this, then as soon as you close the switch, the current, this source will provide the current in the opposite direction. How much current it will provide? Tell me guys. As soon as you close the switch, this source will give the current in opposite direction because minus to plus is upward. So now the current due to the DC source will be negative. Why it is negative? Because it is giving current in opposite direction. And how to write the current? It will be 20 by 10. You can apply the DC transient case now. You should know how to write the current in DC transient. I'm not going to tell you. So 20 by 10 is the steady state current. That is 2 into 1 minus e to the power minus r by omega L. R by omega L omega t. So it will be 10t. Okay. So this is the current due to the DC source only. We can deactivate it and we have only R and L and there is a DC source. As soon as you close the switch, because of this DC source, the current will flow in opposite direction and the equation of the current will be like this. Okay. So this way you can write the current equation. Is it fine guys? So this is my entire current equation. I hope it is clear to everyone. Okay. Those students who don't know how to write the current equation due to the DC source, please watch your DC transient. Okay. I'm not going to tell you from where this current equation came. Okay. Because it's not necessary at this point of time. You should know how to write this DC current equation. Anyway, let's proceed. So I told you how to write the current equation. Okay, why this is important? This equation is important because in some situation we need to look at the maximum firing or minimum firing or just continuous or continuous conduction. There we need the current equation. That's why I'm telling you how to write the current equation. Now in the same question, let's say the switch is not closed at t equal to 0. Let's say the switch is closed at maybe sometime alpha, at omega t equal to alpha. So you are closing the switch at omega t equal to alpha. Now we are not taking it 0. Okay. So omega t equal to alpha, at alpha you are closing the switch now. Now you are not closing the switch at t equal to 0. Let's say you are closing the switch at omega t equal to alpha. Then what will be the equation guys? What will be the current equation? Then the current equation will be IT will be equal to, again, first you have to write the current equation due to the AC source. Due to the AC source, what will be the current equation? First we have to write that. And then we have to write the current equation due to the DC source. Okay. So let's come to the AC source first. So the current due to AC source will be 100 sine of omega t divided by R plus j omega. This is the steady state current. This is the steady state current guys. You can deactivate this 20 volt first. If I deactivate this source, so it will be 100 sine of omega t divided by R plus j omega. Okay. This will be the steady state current. Now what is the value of this? We already know this steady state current value. So why should I write it like this? Better you write the steady state current directly. No? So the steady state current will be, if you write the steady state current, it will be 10 by root 2 sine of omega t minus 45 degree. This will be my steady state current. Now, since you are closing the switch at omega t equal to alpha, so what is the value at omega t equal to alpha? At omega t equal to alpha, this value will be 10 by root 2 sine of alpha minus 45 degree. It means it's not 0. It has some value 10 by root 2 sine of alpha minus 45 degree. It doesn't mean that this value came out to be 0. We don't know the alpha value. Okay. That's why 10 by root 2 sine of omega t minus 45 degree, this value will be, I mean, in general, it will not be 0 at omega t equal to alpha. To make it 0, there will be one current, we call it transient current. And the transient current will be opposite to this value. whatever this value is at omega t equal to alpha, at the closing instant, whatever this value is, opposite to that will be the transient current. So the transient current will be, tell me guys, transient current will be, what is the value of this signal? What is the value of steady state current at omega t equal to alpha? It will be 10 by root 2 sine of alpha minus 45 degree. This is the current. This is the current at omega t equal to alpha. Okay, this is the current at omega t equal to alpha. Value of this at omega t equal to alpha. Now I have to make it 0. So obviously you have to take it opposite. So you have to take it negative of that. Okay, whatever the value this steady state current has, negative of that will be this transient current, and this transient current will decay now. So e to the power minus r by omega l, omega t minus alpha. Why I am writing omega t minus alpha? Because the problem is the current is not starting at t equal to 0. It is starting at omega t equal to alpha. That's why I have to delay it. I have to delay it. Okay. So the current equation will be like this. This is the current due to the AC source only. Now what is the current due to DC source? Due to DC source, the current will be, now you can deactivate it, and the current, because of this 20 volt, the current will start in opposite direction. That's why I have taken minus sign. Minus, what will be the current? 2 into 1 minus e to the power minus, tell me guys, minus r by omega l into omega t minus alpha. Okay, this will be the DC current. Okay, this will be the current due to the DC source. Okay, I don't know how many of you understood this. So it's easy peasy. Tell me guys, tell me, is it clear? So I have written the current equation like this. Those students who don't know how to write this current equation, no problem guys, don't worry, but maybe there are some situations in which you need this current equation. Okay, that's why you need to understand how to write the current equation. Why I have taken omega t minus alpha here also? Because we know that the switch is closing at omega t equal to alpha, so this current will not start at omega t equal to 0. In the previous case, if you are closing the switch at omega t equal to 0, then it is correct. The upper one is correct. You can put alpha equal to 0 in this expression because you are closing the switch at omega t equal to 0 itself. But now you are closing the switch at omega t equal to alpha. It means you have delayed the current. So that's why this current will be delayed and this current will also be delayed. Okay, I hope it is clear to everyone. Sir, how sine 45? How sine 45? Where sine 45? Okay, this impedance, look at the steady state impedance. The steady state impedance is R plus j omega L. Omega is 10, L is 10. So 10 plus j 10. This is my impedance value. This is the steady state impedance of this omega L. So if you take the magnitude, it will be 10 root 2 and the angle is 45 degree. So that 45 degree will come negative here. That's why I have shown 45 degree. Okay. So let's proceed guys. Let's proceed with the next topic. So I told you about the AC transient, how to write the current equation, and in AC transient how to look at this. Okay. Now there are some other situations also in AC transient. And what are those situations? There are some situations like at what time you have to close the switch so that the current remains transient free. Okay, those situations are also there in the AC transient. You can also calculate that instant. How to calculate that instant? Let's revise that part also. So let's say we have a circuit like this. Let's say you have a circuit like this. This is 10 ohm and this is 1 Henry. Okay, and you have a source, AC source here, which is Vm sin omega t. This AC source is 100 sine of omega t minus 30 degree. Okay, let's say this source is provided to you. The source is given. Now we are closing the switch. Omega is given as 10 radian per second. We are closing the switch at t equal to t naught, and the current will be IT. Find t naught such that IT is transient free. IT is transient free. Tell me guys, IT is transient free. We need to calculate the value of t naught such that the current remains transient free. Now how to calculate that? Tell me guys, how to calculate this t naught? Will you do it for me? Will you do it for me? Tell me, at t equal to t naught we are closing the switch. Okay, we are closing the switch at t equal to t naught, and we need to find this T naught value such that the current IT remains transient free. Now tell me how to calculate this how to calculate this T naught. It's very simple. The method is, let me tell you, first you have to calculate the steady state current. So the steady state current, as soon as you close the switch, then the steady state current will be 100 sine of omega t minus 30 degree divided by the impedance value, steady state impedance. Steady state impedance is R plus j omega L. 10 plus j10, not 30. It will be j10. Okay. R plus j omega L. Omega is 10, na? L is 1. So 10 plus j10. This will be my steady state current. So the steady state current came out to be 10 by root 2 sine of omega t minus 45 degree for this impedance. That 45 degree will come in the numerator. It will become minus 75 degree. Is it clear, guys? So we have found that this is the steady state current. Now at t equal to t naught, the omega t value will be equal to omega t naught. At t equal to t naught, instant, omega t will become omega t naught. Now what is the steady state value of this current? The steady state current value at this instant. What will be the steady state current at this instant? Because we are closing the switch at this instant, na? So at this instant, what is the steady state value of the current? So the steady state value of the current will be 10 by root 2 at this instant, na? At this instant, the steady state value of the current will be omega t naught minus 75 degree. This is the steady state current, guys. At this instant, the steady state current is this. If it is not positive, if it is not zero, then there will be a transient current. Why? Why there will be a transient current? If it is not zero, then there will be a transient current. Why? Because the inductor demands zero current. As soon as you close the switch, the net current has to be zero. And we know that this current has two parts, IT steady state plus IT transient. Now, we know this is the steady state part. If it is not zero at the closing instant, at the switch closing instant, at omega t naught, if you put omega t equal to omega t naught, at this instant, if it is not zero, to make this current zero, there will be a transient current. Let's say if it is already zero, then there will be no. Yes, tell me, guys. Is it clear now? Tell me. Is it clear now? Tell me, everyone. Is it clear now? I think it is clear. Okay. So I was telling you that in this situation, if let's say the steady state current itself becomes zero, then there is no need for the transient current. At the closing instant, if steady state current itself becomes zero, then there is no need for the transient current. Okay. So what you can do is, you can make this steady state current zero. Now you can check at what omega t naught this becomes zero. Obviously, whenever this omega t naught will become equal to 75 degree. But in radian, it should be pi by 180 degree. Okay. So whenever this omega t naught becomes this much of radian, at this instant, the steady state current will be zero and there is no need for the transient current. Because this steady state current itself is starting from the zero. Then why we need this? Why we require this transient current? Okay, why we need this transient current? Okay, I hope it is clear to everyone. So now you can calculate this T naught from here. So T naught is equal to 75 pi divided by 180 divided by omega. Omega came out to be 10 value, 10 radian. So you can put 10 in the denominator and you can calculate T naught instant. Okay, at that instant the switch has to be closed. Okay, we should close the switch at T equal to T naught such that the current remain transient free. Anyway, this was again simple question. Now let's proceed with the next topic. So I told you about the AC transient. Okay, I told you about the AC transient. Now there are some important points that I want to tell you is, power factor, input power factor. Let's revise the input power factor topic. Okay, how to calculate the input power factor? In network theory, we usually have pure sine wave, and the current is also pure sine wave. Whenever the voltage is pure sine wave and the current is pure sine wave, you can write the power factor will be equal to cos of voltage angle minus current angle. You can write it like this. This is my power factor. In case of pure sine wave, let's say this is pure sine wave and it has only one frequency. This is also pure sine wave. The current is also pure sine wave and it has only one frequency. Then you can write power factor like this. Okay. But the problem will arise when you have harmonics. Okay. When you have harmonics, whenever you have harmonics, then the problem will arrive, and then we cannot write power factor like this. Okay. Then we have to calculate the power factor. How to calculate the power factor? This is the universal formula for power factor. Active divided by apparent. It means power factor is the factor of apparent power which is active. The factor of apparent power which is active. Okay. We call that power factor. I hope it is clear what is the meaning of power factor. Now, how to calculate the apparent power? Apparent power is RMS value of the source voltage, multiply by the RMS value of the source current. Okay. That product will be the apparent power. So RMS value of this source voltage is Vm by root 2 and the RMS value of the source current is Im by root 2. You just multiply it and you will get the apparent power. Now, how to calculate the active power? Active power, you already know that 1 by 2 Vm Im cos of theta V minus theta. In this case, in this particular case, in case of harmonic, I will tell you. In case of harmonic, I will tell you. But in this case, if you look at this case, in this case, the active power will be 1 by 2 Vm Im cos of theta V minus theta. This is voltage angle theta V minus theta. Okay. So you can calculate. This is my active power. Okay. Now you need to calculate the power factor. So power factor is active divided by apparent. So you can calculate the power factor like this. You can take this ratio. Active is this. This is my active and this is my apparent. If you take the ratio, power factor will be cos of theta V minus theta. You can directly solve it like this. So this is the method by which we can solve for power factor. Now the problem arises when we have harmonics. Let's say you have a circuit. Let's say you have a linear or maybe let's say you have electronic circuit, or maybe let's say it is a circuit. It is not required that this is linear. Okay, let's say we have a circuit and we have some kind of source. Okay, and the source VST has the DC part plus let's say some AC parts are there. Let's say Vm1 sine of omega naught t plus theta V1 plus Vm2 sine of 2 omega naught t plus theta V2. Let's say the voltage contain DC term, AC term with fundamental frequency omega naught and the DC term with frequency 2 omega naught. So voltage source has the harmonics. Now let's say this is my current IST and IST will also have the harmonic. Let's say I0 plus Im1 sine of omega naught t plus theta I1 plus Im2 sine of 2 omega naught t plus theta I2. Let's say this is my current. Now how to calculate the input power factor? I know that input power factor is active power divided by apparent power. Okay, this is my input power factor. Now how to calculate active power first? Let's try to understand active power. Active power can be calculated using Parseval relation. Whenever you have harmonics in voltage and current, use the Parseval relation to calculate the active power. Now what is that Parseval relation? Parseval relation says that the active power will be equal to V0 I0 plus 1 by 2 summation of Vmk Imk cos of theta Vk minus theta Ik. Now what is this expression? What this expression says, k from 1 to n. What this expression says, guys? This expression says that, let's open it. Let's open it for k equal to 1 or k equal to 2, for maybe some 1 or 2 values of k. Let's open it. So it will be V naught I naught plus 1 by 2 Vm1 Im1 cos of theta V1 minus theta I1. This is the first component. If you put k equal to 1, now put k equal to 2. If you put k equal to 2, it will be Vm2 Im2 cos of theta V2 minus theta I2, okay, and plus so on, okay. So there will be so many terms here. Now, if you look at this carefully, you can say that the active power, if you are looking for the active power, then the same frequency component will merge together to form the active power. You can see that the DC component of the voltage is multiplied with the DC component only. The fundamental component, the omega naught frequency term, is multiplied with the omega naught component of the current. Omega naught component of the current. Vm1 is multiplied with Im1. They have the same frequency. Omega naught here, omega naught here. They have the same frequency component. So you can see that the product, voltage and the current product, same frequency component will merge together to form the active power. Whenever you are using the maximum values of the voltage and the current in AC component, this is the AC component of voltage. No? These are the AC components. These are the AC components of the current. Whenever you are using the maximum values of the voltage and current, you have to write 1 by 2 here. So 1 by 2 Vm1 Im1 into cos of angle difference between these two quantities. Theta V1 minus theta I1. For second harmonic, the angle difference between these two quantities, theta V2 minus theta I2. Okay. So this way you can calculate the active power. Just remember, the same frequency component will be merged together to form the active power. You can't say that this component, this fundamental component, will be multiplied with this component and it will make an active power. No sir, it will not make active power. Okay. In active power, same frequency component will be merged together. This way you can calculate the active power. Now how to calculate the apparent power? How to calculate the apparent power? Apparent power can be calculated. In apparent power, you just need to multiply VST RMS into IST RMS. You need to multiply the source voltage RMS value and the source current RMS value. The product will be the apparent power. Simply you can write like this. So apparent power can be calculated using this. I hope it is clear to everyone. Now you can calculate the input power factor. Let's take an example. Let's take an example, guys. Let's take an example to calculate this. Let's say we have this expression, this question. The question is, find the input power factor of the circuit shown below. The voltage VST. This is my VST and the VST value is provided to you. VST is this value, 10 plus 3 sine 2t minus 30 plus 30 degree, and the current IST, this current is IST. IST is provided like this. We need to calculate the input power factor. Can you solve it? Tell me, guys. Please do it fast. Please solve it. Solve this question. Do it fast, guys. Please do it fast and try to calculate the input power factor. Do it fast, everyone. Do it fast. Now you can see that first of all we have to calculate the active power. The active power. How to calculate the active power? Tell me, guys. In the voltage source you have the DC component, but in current you don't have DC component. What does it mean? It means this component will not provide the active power. Because if you remember, I told you that the DC component of the voltage will be multiplied with the DC component of the current, then only it will make an active power. But the current does not have the DC component. If you look carefully, this current does not have the DC component. If this current does not have the DC component, then you can't say that this voltage source, this DC voltage source will provide you some active power. Okay. So this, because of this 10, you have this 10 DC and current component is 0. DC component of the current is 0. Plus, tell me, 1 by 2 into, you can see that the frequency here is 2 and frequency here is 2. So these two components will merge together. These two components will be merged together to form the active power because they have the same frequency. So it will be 1 by 2, voltage magnitude is 3, current magnitude is 1, you can see that, into cos of angle difference. What is the angle difference, guys? Now both are in sine. If both are in sine, you can easily check the angle difference since both quantities are in sine. So the angle difference will be theta v is 30 degree and theta I is minus 30 degree. So if you take theta v minus theta I, it will become cos 60. Okay, it will become cos 60. You can see that. Is it fine? This is my active power. So you can calculate the value. So active power P is equal to, this quantity will be 0 plus cos 60 is half. So it will be 3/4 watt. This will be my active power. I think it is clear. Okay, this is my active power. Now what is the apparent power? We need to calculate the apparent power. So the apparent power is equal to, tell me the apparent power, guys. It is the RMS value of the voltage source multiply by the RMS value of the current source. Multiply by the RMS value of this current. Okay, so RMS value of this voltage source is, you can apply the Parseval relation, DC component square, which is 100, plus 1/2 AC component square, which is 9. Okay, this is my apparent power. This is my voltage source RMS value multiplied by the current source RMS value. Current amplitude is 1, so the RMS value is 1/√2. This way you can write the apparent power. Once you get the apparent power and the active power, you can take the ratio and calculate the input power factor. I hope it is clear to everyone. Okay, so this way you can calculate the input power factor. Tell me, guys, what is the input power factor? So input power factor will be equal to, P by S. This is S, apparent power S. So you can calculate the input power factor. Now you cannot tell whether it is lagging or leading. No, sir. In case of harmonics, you don't define that this power factor is lagging or leading. No, we can't define it. Okay, so I hope it is clear to everyone. In case of harmonic, how to calculate the input power factor? We cannot say that input power factor is cos of theta v minus theta I. No, sir, this is again not valid. Cos of theta v minus theta I is valid only in case you have one component in voltage and the same frequency component in current. There should be only one component in the voltage and one component in the current, and the frequency has to be same. Then only you can say that the input power factor is theta v minus theta I. Otherwise you can't say that. Okay, so whenever you have harmonics like this, then you have to solve it like this. I hope it is clear. Now let's proceed, guys. Let's take one more question. In this question, I need to calculate the input power factor. How to calculate the input power factor? Tell me, guys. Do it fast. Do it fast. Can you solve it? Input power factor. Do it fast. You can calculate this ratio now. You can calculate this ratio in this question. Active is 3/4. Apparent is this. You can calculate this ratio and you will get the input power factor. Okay. Now let's come to the next question. This is the question on your screen. Please try to solve this. Try to solve this question. Do it fast, guys. Do it fast. Do it fast. Let's see how many of you can solve it. For the circuit shown below, current is this and the voltage is this. This is my voltage. Let me give you the amplitude also. This amplitude is 10. Okay, this amplitude is 10 volt. I need to calculate the input power factor. What will be the input power factor? Do it fast. Can you solve it? Can you solve this question? Do it fast, guys. Do it fast. Do it fast. Let's see how many of you can solve it. You have to apply the Fourier series concept, because you know the component in current. There is a DC component, there is a pi frequency component, there is 5 pi frequency component. So in this voltage VIT, we have to look at the frequency component, which component are present and which component are not present. Okay, we have to look at the component in VIT. Then only we will be able to solve this question. Tell me, guys, how to check these components. Tell me. Do it fast. Do it fast. Let's see how many of you can solve it. Do it fast, guys. Okay, let me try, because you are taking so much time. What you can do is, first you expand this VIT. Apply the Fourier series and expand this VIT. What I do is, we know that the average value of this component is 5. We know the average value of this component is 5. So what we can do is, we can subtract 5 from it. So the wave shape will look like this. VIT minus 5. Whenever you have VIT VIT, just subtract the DC component, VIT minus phi. If I subtract the DC component in this wave, then the wave will look like this. 5 and minus 5, it will look like this. It will look like this. Is it clear, guys? Tell me. So this height will be 5 and this height is minus 5. This is 0, this is 1, this is 2, this is 3, 4. Okay. Now we know that this is a square wave, and for square wave we know which harmonics will be present. It contains only odd harmonic sign terms. So VIT minus 5 will be equal to summation of 20 upon n pi sine of n omega naught t. Okay, n from 1 to infinity, and n has to be odd. From signal and system we remember that, we know that whenever you have square wave, so the square wave function, whatever the square wave function, let's call it ft. Okay, then ft can be represented as summation of 4a upon n pi. A is this amplitude, okay, 4a upon n pi sine of n omega naught t, n from 1 to infinity, n should be odd, okay. So I have put this a value, it will become 20 upon n pi sine of n omega naught t. What is omega naught? Omega naught is 2 pi by t, and the time period is 2 itself, okay. So this cancel, omega naught came out to be pi. Omega naught is pi. So you can put this value of omega naught, and then VIT minus 5 will be equal to, if you put n equal to 1, it will be 20 by pi sine of pi t. This will be my fundamental term. N is equal to 1. I have put n equal to 1 and omega naught equal to pi. So this will be my fundamental term. Now the third harmonic, 20 by 3 pi sine of 3 pi t. Next, fifth harmonic, 20 by 5 pi sine of 5 pi t, and so on. Okay. Now what you do is you take this 5 on this side, because minus 5 is, because we are looking for VIT. We are not looking for VIT minus 5. So take this 5 on this other side. If you take this 5 on the other side, then it will become VIT equal to 5 plus this. Okay. This will be my VIT now. So we know the value of VIT. We know the value of VIT now, and we know the value of IT. Now you can see that this current has the DC component, and the voltage will also has the DC component. So what we can do is, first let's calculate the active power. What is active power, guys? Can you tell me the active power? What is active power? So active power will be equal to, look at the DC component first. The current has the DC component as well as the voltage has the DC component. So you just multiply them. If you multiply them, you'll get 10. 10 plus. Now look at the AC component. In the AC component, you have sine terms here, and a pi term and 5 pi term. Only 2 terms are there in the current. So only 2 terms are important. This term and this term. Only 2 terms are important in AC. This pi term and this 5 pi term. Why they are important? Because they have the same frequency. Now the current has the pi component and 5 pi component. So same component, pi and 5 pi are important, because in voltage we have this 3 pi term, but in current we don't have the 3 pi term. I told you in active power same frequency component will participate. Okay. So you can say that this component will not participate in active power. Moreover, the next component, the 7 pi or the 9 pi or the 11 pi, those components will not participate in active power. Now what will be the active power? So how to calculate the active power? It is V naught I naught DC, just multiply the DC component plus 1 by 2 the AC component. The peak value of this AC component is 3, multiply by the peak value of this AC component is 20 by pi into cos of angle difference. What is the angle difference, guys? Here you have minus 30, here you have 0. Okay, and both quantities are in sine. Both quantities are in sine. So the angle difference is minus 0 minus 30. 0 minus or minus 30, it will become plus 30. Even in cos, whether it is you take plus 30 or minus 30, it doesn't matter, because you are taking cos. Okay. So this is the V1 I1 cos of theta V1 minus theta V1. Now let's come to the next component. So the next component, in current you have 80, in voltage you have 20 by 5 pi. So what you can do is you can write 20 by 5 pi, this is the voltage peak value, into the current peak value is 80 into cos of angle difference. Now how to look at the angle difference? This is a cosine wave and this is a sine wave. To check the angle difference, what you need to do is you need to make both of them either in sine or either in cos. Now what we can do is we can convert this in sine. So it will be 80 sine of 5 pi t minus 45 plus 90. Tell me guys, whenever you convert cos into sine, you just add 90 to it. Whenever you convert cos into sine, you just add 90 to it. Is it fine? So now it will become 80 sine 5 pi t plus 45 degree. You can see that. Okay, and this quantity is 20 by 5 pi sine 5t. So we have this magnitude voltage 20 by 5 pi into 80 into cos of angle difference. The angle of this quantity is 0 and the angle of this quantity is 45 degree. So if you take the difference, it will be minus 45 degree. Okay, it will be minus theta v minus theta I. And there will be no other quantity. Only two quantities will be there. Because in current we have only two quantities of AC. That's why we need to take only two quantities. This way you can calculate the active power. Now what is the apparent power? How to calculate the apparent power? Apparent power will be equal to RMS value of this current multiplied by the RMS value of this voltage. Okay. Now how to calculate the RMS value? RMS value of this current can be calculated as root of DC component square, which is 4 plus 1 by 2 into 9 plus, this is 9 plus 80 square. 80 square is 6400. Okay. This will be my RMS value of the current into the RMS value of the voltage. So what is the RMS value of this voltage? The period is 2. So we can calculate the RMS value. So RMS value will be root of 1 by 2 integration 0 to 1. 0 to 1 it is 10 square dt. Okay, this way we can calculate the RMS value of this voltage, and the RMS value of this current, multiply them together. So you'll get the apparent power. Once you get this active power and apparent power, the power factor will be, input power factor will be equal to the ratio P by S. Okay, this is my P, this is my S. Is it clear guys? So this way we can solve it. Sir, in denominator 3 is there. Where we have 3? It should be 5 here. It should be 5 here. Because this is the fifth harmonic. 3 is there in the third harmonic. Okay. We are not looking at the third harmonic. Why? Because third harmonic means 3 pi frequency term. There is no 3 pi frequency term in this current. That's why. Okay. Let's proceed guys. Let's proceed. Whenever you need to analyze the wave, then you need this quarter wave symmetry. Maximum wave which you are going to encounter in power electronics, especially in inverter, they will be quarter wave symmetric. Whenever you have quarter wave symmetry, then you can calculate the fundamental amplitude or third harmonic amplitude or fifth harmonic amplitude directly. Okay. Now how to calculate the fundamental third and fifth amplitude directly? Using the quarter wave symmetry. What is the quarter wave symmetry guys? Whenever any wave is odd or even. Let's say we have a signal, we have a voltage signal or current signal which is either odd or even, and it also contains odd half wave symmetry. Then it will become quarter wave symmetry. It also contains odd half wave symmetry, then we call quarter wave symmetry. Okay, this will give us quarter wave symmetry. Now it is important. Why it is important? Because let's say there is a wave. And the wave is like this. Let's say you have the wave like this. In inverter you will encounter these type of waves. Now tell me, what is the nature of this signal? Omega t, let's take it, or maybe t you can take, whatever. Okay, 0. This is pi by 2. Okay, and let's take it pi by 3. Okay, this is pi by 3, this is pi by 2. This is 2 pi by 3, and this point is pi. This height is 5 and this height is 10. Let's say we have a voltage signal. We have a voltage signal like this, and this axis is omega t. what I need to do is I need to find third harmonic amplitude. Third harmonic amplitude. Now, how to calculate the third harmonic amplitude? Tell me guys, how to calculate the third harmonic amplitude? First of all, please tell me what is the nature of this signal. Is it odd or even? Tell me guys, is it odd or even? This signal is odd, obviously. If you plot it in the negative side, it will be like this. So you can see that this signal is symmetric in opposite quadrant. So this signal is odd. This signal is odd, that's correct. Plus, this signal contains odd half-wave symmetry. This signal also contains odd half-wave symmetry. If the signal is odd and also contain the odd half-wave symmetry, then it will make quarter-wave symmetry. Whenever the signal has quarter-wave symmetry, we can calculate amplitude of any harmonic, third or fifth or seventh or whatever. Okay, we can calculate the amplitude of any harmonic. How to calculate that amplitude, guys? It can be written as, let's say we want to calculate the third harmonic amplitude. So V03 will be equal to 4 by pi integration 0 to pi by 2. Just look at the 1 quarter. Just look at this 1 quarter. We are interested in 1 quarter only. So 0 to pi by 2, whatever this function Vt into sine of 3 omega naught t d omega naught t. Okay, you have to integrate this. Wherever you want to calculate the peak value of the third harmonic amplitude, you can write it like this. Let's say you want to calculate the peak amplitude of fifth harmonic amplitude. Let's say you want to calculate the fifth harmonic amplitude. Okay, so the fifth harmonic amplitude will be 4 by pi 0 to pi by 2 under 1 quarter. This is 1 quarter. This is 1 quarter because the full period is 2 pi. So half period is pi by half period is pi. So 1 quarter is pi by 2. So just look at 1 quarter. So it will be 0 to pi by 2 Vt into sine of 5 omega naught t into d omega naught t. This way you can calculate the amplitude of the fifth harmonic. Is it clear, guys? If the signal has quarter wave symmetry, you can directly calculate the amplitude. Now why you have taken sine here? Because the signal is odd. Let's say the signal is even. Let's say the signal is even and it contains odd half wave symmetry. Then again it will be quarter wave symmetric. But then to calculate the amplitude of third and fifth, I have to take cosine here. In place of sine, you have to take cosine here. Is it fine? So this way you can apply the concept and you can calculate the amplitude. Now let's calculate this third harmonic amplitude. So it will be 4 by pi. Now in 0 to pi by 2, if you look at 0 to pi by 2, then this voltage is changing. This voltage is from 0 to pi by 3 it is 5 and from pi by 3 to pi by 2 it is 10. So what you can do is we can break this integration. We can break this integration from 0 to pi by 3. From 0 to pi by 3, this Vt is 5. So you can write 5 sine of 3 omega naught t d omega naught t. Okay, plus from pi by 3 to pi by 2. From pi by 3 to pi by 2. From pi by 3 to pi by 2, this Vt is 10. So it will be 10 sine of 3 omega naught t d omega naught t. Okay, so this way we can solve it. This way we can calculate the peak value of the amplitude of the third harmonic. Okay, now we can solve this and calculate the amplitude. Is it clear, guys? So that's why this quarter wave symmetric is important, because whenever you have quarter wave symmetry, you can directly calculate the amplitude of any harmonic. Okay, you can calculate the amplitude of any harmonic. Why you need to calculate the amplitude of any harmonic? Because there are some situations in which it asks maybe some THD, total harmonic distortion. Okay, let's say in this question, if it asks what is the total harmonic distortion, then we need to calculate the amplitude of the fundamental, because in the formula of total harmonic distortion, we need to know the amplitude of the fundamental component. Okay, what is total harmonic distortion? How to calculate the total harmonic distortion? I'll tell you, but before that, let's take this question. The question is, given that Ft contain odd half wave symmetry, also the Ft is odd signal. It is given that this signal is odd. the signal is odd plus it contains odd half wave symmetry. It means the signal has quarter wave symmetry. Is it fine, guys? The signal has quarter wave symmetry. We need to calculate third and the fifth harmonic amplitude. Okay, how to calculate the third and the fifth harmonic amplitude, guys? Tell me, this is alpha 1 and this is alpha 2, this is pi by 2. It means 1/4 is given. 1/4 is given. Pi by 2 means 1/4. There is only 1/4 is given. Okay, because whenever you plot the signal in omega t axis, then period is always 2 pi. Period is always 2 pi. So since the signal is given as pi by 2, so you can say that ft is plotted under 1/4. So this is 1/4 wave. 1/4 signal is provided to you. What we need to do is we need to calculate the amplitude of third and the fifth harmonic. How to calculate the amplitude of third and fifth harmonic? It's very simple. What you can do is you can apply quarter wave symmetry, that is 4 by pi integrate from 0 to pi by 2, whatever the voltage is, whatever ft is, ft into sine of 3 omega naught t. 0 to pi by 2 ft into sine of 3 omega naught t d omega naught t. You can calculate the amplitude of the third harmonic like this. Okay, this will be amplitude of the third harmonic, or maybe ft, f naught 3, whatever you can write. Don't write it voltage, because this is not voltage signal, this is some function ft. So it will be third harmonic peak value. Okay, so you can calculate this. How to calculate this? Because we know that from 0 to pi by 2 the function has different values. From 0 to alpha 1 it is a naught, from alpha 1 to alpha 2 it is minus a naught, from alpha 2 to pi by 2 again a naught. So what you can do is you can break this integration. So it will be 4 by pi. Now you can break it from 0 to alpha 1. From 0 to alpha 1 the function is a naught sine of 3 omega naught t d omega naught t, and then plus alpha 1 to alpha 2. Tell me, guys, from alpha 1 to alpha 2 it is minus a naught sine of 3 omega naught t d omega naught t. Okay, plus from alpha 2 to pi by 2 again a naught sine of 3 omega naught t d omega naught t. This way you can calculate. Okay, you need to solve it in terms of alpha 1 and alpha 2, you will get the answer. So the answer came out to be 4 a naught by 3 pi 1 minus 2 cos alpha 1, 2 cos 3 alpha 1 plus 2 cos 3 alpha 2. You can check it. Okay, so this will be the answer. This will be the peak value of the third harmonic amplitude. Now what will be the peak value of the fifth harmonic amplitude? Again, in place of 3 you can place it 5. Okay, replace this 3 with 5 and you will get the peak amplitude of the fifth harmonic. So it will be 4 a naught upon 5 pi 1 minus 2 cos 5 alpha 1 plus 2 cos 5 alpha 2. Okay, this will be the amplitude of the fifth harmonic. It's easy peasy. I hope it is clear to everyone. Now we can proceed. So I told you what is the advantage of quarter wave symmetry. Using the quarter wave symmetry, you just take 1/4 only. If you are solving the same question taking the entire period, then it will be very difficult to solve. It will be very difficult to calculate the amplitude of the third and the fifth harmonic. Okay, because many students think that, sir, if I need to calculate the third harmonic amplitude, why don't I replace it? We know that there is a bn component in this. An is 0, cosine terms component is 0, only the sine terms will be there. So bn, we can write it like this, na? 1 by t or maybe 2 by t 0 to t ft into sine of n omega naught t dt. We can write it like this. This is my bn, the formula for bn, the amplitude, nth harmonic sine term amplitude. So if you are writing like this, then you have to integrate for entire period. It's a very lengthy process. That's why I told you the quarter wave symmetry, because in many places in power electronics, in many places, especially in inverter, you will see the waves which has quarter wave symmetry. So there you can apply this concept and you can calculate that. Okay. Now let's come to the distortion. I told you what is percentage THD. Sometime we need to calculate the total harmonic distortion, percentage THD. Okay, now what is that? How to calculate that? Let's say we have a function ft. So ft contains the DC component and the fundamental component and the higher order harmonic. Assume this function as ft. Take this function as ft. If you take this function as ft, then it will have some DC component or fundamental. There is some fundamental term also, and it will contain the higher harmonics. Okay, higher order harmonics it will also have. Now we need to calculate the THD, percentage THD. How to calculate? What you need to do is first you calculate the RMS value of this function ft. RMS value of the entire function ft. Okay, you can calculate the RMS value like this, or you can use the graphical method. You can use this formula also to calculate the RMS value, 1 by t integration 0 to t ft square dt. Okay, you can use this formula also to calculate the RMS value of the function. So we know the RMS value of the entire function. We know the RMS value of the entire function. Now what I need to do is, this is my ft, this is my total function ft, and this is the expression for the entire RMS. What we need to do is, we need to look at the RMS value of DC and the higher order terms. We want to eliminate this. We want to remove this fundamental. It means the total function ft minus the fundamental. We want to check the RMS value of ft minus fundamental. It means what will be the RMS value if we remove this fundamental component in the ft. Then how to check that RMS value? That RMS value will be the total function RMS value, take the square of that, minus only the fundamental component RMS value. Fundamental component RMS value, and take the root of this. Now this represents the distortion, because if you have removed this fundamental, apart from this fundamental, everything is distortion. Okay, apart from this fundamental component, everything is distortion. What is the RMS value of the distorted wave? So the RMS value of the distorted wave is the total RMS value of the function, the total function RMS minus the RMS value of the fundamental component. This way you will get, and take the root. This way you will get the RMS value of the distortion. Now what is the percentage distortion? How to calculate the percentage value of this? So what you can do is, you can check this RMS value, how much percent this RMS value is with respect to fundamental RMS. What is this value? With respect to the fundamental RMS, what is this value? Okay, so you can calculate this ratio. We call it percentage total harmonic distortion, or THD, percentage THD. Just multiply with 100. Okay, this way you can calculate the distortion. So now if you want to calculate the distortion, you need to calculate the RMS value of the fundamental. Now how to calculate the RMS value of the fundamental? Once you get the peak value of the fundamental, divide it by √2. Once you get the peak value of the fundamental, let's say you want to calculate the total harmonic in this case. You want to calculate the percentage harmonic distortion in this case. So what you need to do is, you need to calculate the fundamental component, peak value of the fundamental. I told you how to calculate the peak value. For calculation of the peak value, you take 1 omega naught t here. Okay, in place of 3 you take 1. You will get the peak value of the fundamental component. Divided by √2, you will get the RMS value of the fundamental component. Once you get the RMS value of the fundamental component and the total RMS value of the function, total RMS value of the function can be calculated using the graph. Using the graphical approach, you can calculate the total RMS value. So total RMS value, take the square of this minus the RMS of the fundamental component square, divide by the fundamental component. This way you can calculate the percentage THD. Okay, so I told you why you require the quarter wave symmetric method. Okay, why you require this quarter wave symmetry? Because you can calculate any harmonic amplitude now. That's why it is important. So I told you. Now let's check this current distortion factor. What is this current distortion factor? Let's say you have a current wave. Let's say this is some electric circuit, and this is my VST, and we have a current wave. Okay, and the current has harmonics. It has DC component, IS1 sine of omega t minus theta I1 plus higher order harmonics. Okay, so current has harmonics. Let's say this is my IST. Let's say this is my IST, the source current. Okay, now what we can do is, the current we need to understand the current distortion factor. How to calculate the current distortion factor? Look at the input power factor first. What is the input power factor? So the input power factor is, we know that the voltage contain only the fundamental term. It may contain harmonics also, it doesn't matter. So let's say it contain only fundamental. Let's take it fundamental only. So if you take the fundamental component of the voltage and the current has harmonics, then first of all calculate the active power. Since the current has the DC component but voltage does not have the DC component, so the active power will only be due to the fundamental component only, okay, because the voltage has only fundamental. That's why this fundamental component only will participate in active power. Now tell me the active power. It will be 1 by 2 peak value of this voltage, which is Vs1, into the peak value of the current Is1 into cos of theta V minus theta I. Theta V is 0 and theta I is minus theta 1. Okay. So I have calculated the active power. Now what is the RMS, the apparent power? This is my apparent power. Apparent power is Vs RMS into Is RMS. You just multiply the RMS value of the voltage and the current and you will get the apparent power. Once you get the apparent power and the active power, what you can do is you can take the ratio and calculate the input power factor. So the input power factor came out to be this value. Okay. Input power factor is active divided by apparent. Now if you look at this carefully, what I have done is, these are the peak value. Vs1 and Is1 are the peak value. So you can write it like this. You can write it like this. This is Vs1. Vs1, this is the peak value, no? So what I need to do is, you can take it RMS value, Vs RMS value. Okay, wait a minute. Whenever you take R maximum value, you have to take 1 by 2 factor. But if you are taking RMS value, Is1 RMS into cos of theta I. Whenever you take RMS value, voltage RMS value into the current RMS value, okay, into cos of, then you don't need to take 1 by 2. You don't need to take 1 by 2. Okay. So what I have done is, I have taken the RMS value of this signal and RMS value of the current, the fundamental RMS value of this component, okay, cos of theta I. This will be my active power. So what you need to do is, you need to take the ratio. If you take the ratio, then what will be the ratio? Tell me guys. The ratio will be, you can see that, don't look at this, just look at this. Vs RMS into Is1 RMS cos of theta I divided by this value. So if you divide it by this value, you'll get this value. You can check it. If you divide it by this value, this Vs RMS will cancel and you will get Is1 RMS divided by Is RMS into cos of theta I. This you will get. This is my input power factor. Now, this factor, we call it current distortion factor. Okay. This is the current distortion factor. Now, many of you will not remember this. So let me tell you directly. What is current distortion factor? So current distortion factor is equal to, let's say you have a current wave shape. Let's say current is like this. Let's say the current is like this. This is my current wave. Okay. Let's say this is A naught. This is minus A naught. This is T by 2 and this is T, let's say. So what you need to do is to calculate the current distortion factor, that is calculate the fundamental component. Whether you take RMS value or the peak value, it doesn't matter because you are taking the ratio. So the fundamental component of this current, take the fundamental component, divide by the total current RMS value. Fundamental RMS divided by the total RMS, or fundamental peak divided by the total peak. If you are taking the peak value, then you have to take the peak, both the peak you have to take. Okay. Otherwise, what you can do is better you don't take peak, you take RMS always, because peak will sometime create some problem. So better take RMS ratio. Okay. The fundamental RMS value of this current divided by the total RMS value of this current. Okay. This is the current distortion factor. Remember, we call it current distortion factor. Now, what is this cos theta I1? It is the displacement power factor. We call it displacement power factor. Okay. Displacement power factor. It is not the actual power. It is not the true power factor. So current distortion factor into the actual power factor, into the current distortion factor into the displacement power factor will be the actual power factor. Okay. This is my actual input power factor. Okay. So please try to understand this. What is the current distortion factor? So I told you how to calculate the current distortion factor. So there were some current distortion factor or total harmonic distortion. Okay, so these 2-3 terms are very important. Sometimes they ask you. Now let's come to the next topic, and that is the diode circuit. Now in diode circuit there are so many circuits like inductive load, R load, RL load, half wave rectifier, full wave rectifier. Okay, but what I have selected is this question because I don't want to revise the diode circuit because it's not necessary. We will jump to the Thyristor circuit only, but first let's revise the diode part. So tell me, what should be the answer for this? The question is, consider the circuit shown in the figure. If the switch is closed at t equal to 0, we are closing the switch at t equal to 0 and open at t equal to 2 seconds. Analyze the voltage and the current in each branch of the element. Okay, we have to analyze the wave shape of the current and the voltage. Now tell me what should be the wave shape? We have a DC supply, so it's very simple. You can see that these two diodes are under common cathode configuration. Their cathode is common. Whenever two diodes are under common cathode configuration, the diode which has the highest voltage on anode will conduct. The diode which has the highest voltage on anode will conduct. So what you can do is, let's assume that this is 0. Let's assume that this is 0 volt. As soon as you close the switch, this will become 20 volt. Fine. Because this, if this is 0, this will be 20 volt. So this point will be at 20 volt. So as soon as you close the switch, this will be 20 volt, this is 0 volt. Now tell me, you have two diodes, one is D1, one is D2. One is D1, one is D2, and you have 20 volt at the anode of this side, anode of this diode, and you have 0 volt on the anode of this. Which diode will conduct? Since they have since these two diodes are under common cathode configuration, the diode which has the highest voltage on anode will conduct. That's why D1 has to conduct. So as soon as you close the switch, D1 will conduct and the current will flow like this. Current will flow like this. The circuit is RL and you are applying DC. So current will rise exponentially. Current will rise exponentially. Is it fine? Current will rise exponentially from 0 to 2 seconds. From 0 to 2 seconds, current will rise exponentially. If you want to plot this current I naught T, then I naught T will rise exponentially, and at t equal to 2 seconds you are opening the switch. If you have opened the switch, since the inductor has built up some current, if you have opened the switch, then there is only one path. Via this path, the diode will become forward bias now. This diode will become forward bias now, and the inductor current, whatever the current has built up in this inductor, that inductor current will freewheel through this diode. This inductor current will freewheel through this diode. So it means the current will decay exponentially. Now the current will decay exponentially. Is it fine, guys? This is the current wave shape. Now the question is 0 to 2 D1 will conduct, and after 2 D2 will conduct. Now the question is, what is this peak value? How to calculate the peak value of the current? How to calculate the peak value of the current? Tell me, guys, how to calculate the peak value? You have to write the current equation. When this switch was closed, you have to write the current equation. Can you write the current equation directly? Yes, we can write it. 20 by 4, that is 5 into 1 minus e to the power minus r by lt, r by l. R is 4, L is 2, so it will be minus 2t. Okay, this will be the current equation, guys. This will be the current equation. You can see that at t equal to 0, it is 0. At t equal to infinity, it will go to 5. But we will not go to up to t equal to infinity. At t equal to 2, we need to calculate. So we can put the value t equal to 2 in this equation. So it will be 5 into 1 minus e to the power minus 4. Okay, this much of ampere will be this peak value of the current. Now many students don't know how I have written this equation. If you don't know this, how I have written this expression, then please revise your DC transient. Okay, using the DC transient you can understand that. So this will be the current wave shape. During this interval diode D1 is conducting, and during this interval diode D2 is conducting. Okay, so this is the current wave shape. You can plot it easily. This is direct transient equation. This is my transient, wait a minute. Yes, this is my transient equation, nothing else. Okay, let's come to the next topic. Next is this question. Please do it, guys. Please try to solve this question. I'm giving you 2 minutes. Do it. Let's see how many of you can solve it. This is again very good question. Consider the circuit shown in the figure below. The switch S is closed at t equal to 0. Okay, we are closing the switch at t equal to 0 and opened at t equal to t naught. At t equal to t naught we are opening it. Okay, find t naught if this IFD is 10 ampere at t naught 0 plus. At t naught 0 plus, this IFD is 10 ampere. We need to calculate this t naught value. Do it fast. Tell me guys, what is this t naught? Do it fast. Do it fast. Do it fast, guys. Again, it's a DC transient. It's a DC transient. You can directly solve it. Do it fast, guys. Please try to solve it. You have 2 minutes. Do it fast, do it fast. What should be the answer? Tell me, guys. Thank you, Ashok. What should be the answer, guys? Tell me. And like this session, guys. Don't forget to like this session. Those students who haven't liked this session, please like it. Okay. Please like the session and tell me the answer. What should be the answer? Do it fast. What should be the answer? Tell me what should be the answer. Okay, let's see. Tell me in which configuration these two diodes are connected. Common cathode. Their cathode is common. Whenever the common cathode configuration, whenever diodes are connected in common cathode, then the diode which has the highest voltage on anode will conduct. Now you can assume that this is ground, this is 0, and as soon as you close the switch, this voltage will become 10 volt. Now tell me which diode will conduct. Obviously this diode will conduct. This D1 will conduct. Okay, so now you can see that if D1 is conducting, it will be sorted. So the voltage across this inductor will be this 10 volt directly. Okay, this will be sorted and this 10 volt will be the voltage across this inductor. We have an ideal inductor. Across ideal inductor, if you have a constant voltage, then this current I naught will rise linearly. You can apply the Laplace transform. Current will rise linearly. What should be the equation of the current? IT will be equal to, initial current was 0 plus 1 by L integration 0 to t, and the voltage across the inductor is 10. Is it clear, guys? This will be the current. This will be the current I naught t. Okay. So now you can calculate that this is 5t. This is 5t. So it means this equation is 5t. This equation is 5t. So we need to reach to 10 ampere. We need to reach to 10 ampere now. So we can see that at t equal to t naught, which is equal to 2, okay. So at 2 seconds, it has reached to 10 ampere. Now what will happen after 2? After 2, you are opening this switch. If you have opened this switch, what will happen, guys? If you have opened this switch, if the switch is opened, then what will happen? Then the build-up current, the inductor has stored some current, no? 10 ampere it has stored. That current will flow through this diode, okay. So you can see that the voltage across the inductor will become 0 because it is sorted. So the voltage across inductor will become 0. It means the current will remain constant. Whenever the voltage across inductor is 0, what does it mean? Whenever the voltage across inductor becomes 0, if this is 0, it means the current IT is constant. Okay, it means the inductor current will remain constant at this value. So you can see that the current will remain constant at 10 ampere. So what is the time? What is the t naught time at which the switch is open? So it should be 2 seconds. Okay, it should be 2 seconds. You can see that because it has to reach to 10 na, and this equation is 5t. So to reach to 10 ampere, it will take 2 seconds. Just after 2 seconds, you open it. You open the switch. So the 10 ampere will circulate here. And at t equal to t naught plus, the current remain as 10. Okay. I hope it is clear. Answer is 2 seconds. Let's come to the next thing. Okay. Now, I want to look at the effect of the source inductance. Let's say you have this 5 ampere. Let's solve a question. Let's say you have 5 ampere. And this inductance, let's say this is the source inductance. This inductance is 0.05 0.05 Henry or maybe 0.5 Henry. Let's take it 0.5 Henry. 0.5 Henry, okay? And this is, let's say, 50 sine of 10t. This is 50 sine of 10t. What I need to do is, I need to calculate this V naught t. V naught t average. What is this V naught t average? With and without this inductance. With and without this inductance. First take the effect of this inductance. First don't take the effect of this inductance. Take it L equal to 0 and then take the inductance effect. Okay. And we need to analyze what will be the average output voltage in both the situation. How to calculate? First, let's not consider this voltage, this inductance. If you are not considering this inductance, the circuit will look like this. Ls is 0. I am taking this Ls source inductance. I am taking it 0. Okay, so the circuit will look like this. The circuit will look like this. You have a constant current of 5 ampere. You have a constant current of 5 ampere and you have this AC source. This AC source is 50 sine 10t. 50 sine 10t. Okay, we need to analyze this voltage V naught t. And then we need to calculate the average value of V naught t. How to calculate that? Tell me guys. Let's call it D1, let's call it D2 and let's assume that this is grounded. So this voltage is 0 and this voltage is supply voltage VST. Whatever this supply voltage is, don't look at the sine wave, just look at this, this variable VST. So if this is 0, this will be VST. Now we have two diodes D1 and D2. In which configuration these two diodes are connected? Tell me guys. In which configuration these two diodes are connected? These two diodes are connected under common cathode configuration, common cathode. So the diode which has the highest voltage on anode will conduct. This is my VST. This is my VST. Now you can see that from 0 to pi radian, I am plotting this with omega t axis. I am not plotting with time axis. I am plotting with omega t. So whenever omega t is pi, omega t is this 10t. Omega t is 10t. So at whenever this omega t is pi, it will be 0. Whenever it is 2 pi, it will be again 0. At 3 pi, it will be again 0. Okay. And this peak value is Vm. Now, we are interested in plotting the output voltage V naught t. We need to plot this output voltage V naught t. How to plot it? How to plot this output voltage V naught t? For that, we know that this diode D1 will conduct. This diode D1 will conduct if the anode voltage is higher than the 0 voltage. Because we know that these two diodes are connected in common cathode. So whenever this VST is positive, 0 to pi, you see, 0 to pi, you can see that from 0 to pi, this is positive and this is 0. This is 0 volt, this is positive. So you can see that since it is positive, diode D1 will conduct because it has the higher voltage on anode. So diode D1 will conduct, it means it is sorted. If it is sorted, the output voltage will be same as the supply voltage. The supply voltage source will come in parallel with the current source. So you can say that the output voltage will be same as the supply voltage. Okay. From 0 to pi, the output voltage is same as the supply voltage and this peak value is Vm. Okay. Now what will happen from pi to 2 pi? From pi to 2 pi, what will happen? From pi to 2 pi. From pi to 2 pi, this voltage is negative and this is 0. Which one is higher? 0 is higher. It means now this diode will conduct. So the current will freewheel here and the output voltage will become 0. Output voltage will be 0 from pi to 2 pi and then from 2 pi to 3 pi. Again the supply voltage is positive. Here you have the positive voltage. So again D1 will be sorted and the output voltage will be same as the supply voltage. It will come in parallel with the output. The supply voltage source will come parallel in the output voltage. Okay. Parallel with the output voltage. So this will be my wave shape of output voltage. I hope it is clear. Okay. I hope it is clear. So now what is the average voltage? So the average voltage V naught T average came out to be Vm by pi. Okay. Vm peak value is given as 50. So 50 by pi. 50 by pi will be the average value in this situation. In this situation, this is my average output voltage. Now, what I'm doing is I'm connecting a source inductance. If you are connecting a source inductance, then the circuit will look like this. Let me redraw the circuit now. The circuit will look like this. Now you are taking the source inductance. Now it is very important. Now the circuit will look like this, and this is 50 sine of omega t. Omega is 10, so I'll put the value of omega later. Okay, this is 5 ampere and this is Ls. Now Ls is 0.5 Henry, right? 0.5 Henry. Okay, and we want to analyze this V naught t. Okay, so let's try to analyze it. You can see that this axis is omega t and the supply voltage is like this. This is my supply voltage. It's a pure sine wave, and before 0 it was negative. Okay, and this value is maybe 50. Now you can see that before 0, can you tell me which diode was conducting? Before 0, obviously D2 was conducting. Before 0, entire current was flowing through D2, so the output voltage was 0. Now I want to see 2-3 things. One is the source current IST, this source current IST, and one is this output voltage V naught t. So now you can see that before 0, the freewheeling diode was conducting. This diode was conducting. The current was freewheeling because this voltage was, let's take it 0 now. Let's assume that this is 0 and this is VST. Tell me guys, is it clear now? Tell me, is it clear? Is the video clear? Tell me, is the video clear? Okay, I suppose it is clear now. Okay, so I told you, look at this circuit. Look at this circuit. In this circuit, this is my supply voltage. Okay, I want to look at the source current IST and the output voltage V naught t. So we want to analyze output voltage and the source current. Now this is 0, this is pi, this is 2 pi, this is 3 pi. So I told you that before t equal to 0, this source was negative voltage. Source voltage was negative. So this point voltage was negative. So the current was freewheeling through this diode D2. The current was freewheeling through this diode D2. Fine. So the output voltage will remain at 0. Before t equal to 0, the current was freewheeling. It means the output voltage will be 0. So you can see that output voltage will be 0. Let me show the output voltage with the white pen. Wait a minute. Before 0. I need to show it before 0. Okay. So before 0, the output voltage was 0 and the source current was also 0. The source current was also 0. Why? Because there was no source current. Current was freewheeling here. So it was sorted and the output voltage will be 0. Now, after t equal to 0, what will happen? After t equal to 0, this is positive now. If this voltage is positive, then this diode has to conduct. But inductor was there now. Inductor is there now. Due to this inductor, the current will not abruptly shift to this side. Current will not abruptly shift to this side. In the previous case, let me show the current also. In the previous case, if I want to show the current also, the source current. In the previous case, let me show you the current also, the source current IST. We can see that as soon as it becomes positive, as soon as the supply becomes positive, diode D1 start conducting and this 5 ampere start coming from this side. So it means from 0 to pi, the source current will be 5 ampere. Source current will be 5 ampere. Now from pi to 2 pi, again the freewheeling diode will conduct and the current will become 0. And then from 2 pi to 3 pi, again the diode D1 is conducting. It means the current, this 5 ampere will flow through D1 and abruptly the current will change to 5 ampere. Is it fine? This will be the shape of the source current. This will be the shape of the source current in the previous case, in this case. But now in this situation, what will happen is, before 0, the current was freewheeling everywhere and the inductor current, the source current was 0. This current was 0. Now, after 0, what will happen? After 0, it is positive. This voltage is positive. If it is positive, this diode D1 has to conduct. But the problem is, it has inductor. At its anode, it has some inductor. And in inductor, current cannot change abruptly. In the previous case, current changed abruptly because there was no inductor. But now the problem is, it has inductor and inductor has initial current 0. So the current will not change abruptly. So slowly the current will increase. So here the current will increase slowly. It means it requires a constant current because the current source needs 5 ampere fixed. This current is slowly increasing. So it means this current has to decrease slowly, so that the resultant becomes 5. Resultant remain constant. Because of the inductor, this current will decrease slowly, and this current will increase slowly, and this current will decrease slowly. So it means for some time, for some mu interval, both the diodes will conduct, this diode and this diode. This current will decrease and this current will increase. So there will be overlapping. There will be overlapping of both the diodes. It means both the diode will conduct. For some time, both the diodes will conduct. This current will increase slowly, this current will decrease slowly. Eventually, it will become 0 and it will become 5 ampere. That time in which this current will reach to 5 ampere, that time I call overlapping interval, mu. During this interval, this source current will increase. This source current will increase to 5 ampere. Is it fine? It will increase like this. It is not straight line. Okay? It will increase like this. The source current will increase like this. And since the diode D2 is still conducting, output voltage has to be 0. Up to this mu interval, output voltage has to be 0 because the freewheeling diode is still conducting. Is it clear, guys? Have you understood it? Up to this time, I think there is no problem at all. Okay? So up to this mu interval, the freewheeling diode has to conduct, and this current, this source current has increased from 0 to 5 ampere. Now, what is this mu interval? How to calculate this mu interval? We know that during this overlapping interval, both the diodes are conducting. So if I want to make the circuit diagram, if I want to analyze this circuit, the circuit will look like this. This D1 is sorted and the D2 is also sorted. Okay? And you have a current source of 5 ampere. You have a current source of 5 ampere. Fine. And there you have a source voltage VST. Here you have the source voltage VST. Now, we know that this current is increasing, this current is decreasing. Now, how to analyze this situation where this current is increasing and this current is decreasing? What you can do is, you can imagine the mesh current. You can imagine that there is a mesh current I mu. This I mu is same as the supply current IST. During this overlapping interval, this circuit is valid only between 0 and mu. Remember, this circuit is valid only between 0 and mu. Why? Because both the diodes are conducting only during this interval. So during this interval, both the diodes are conducting. This current is increasing, this current is decreasing. So how can you imagine that? You can imagine that there are two meshes. Okay? You can imagine that there are two meshes. In one mesh, you have 5 ampere. And in one mesh, you have I mu current. So you can imagine like this. Now you can see that this diode current is 5 minus I mu. And this diode current is I mu. D1. Diode D1 current is I mu. Diode D2 current is 5 minus I mu. What is this I mu? I mu is the source current IST. I mu is the same as the source current. You can apply the mesh analysis now. I mu is the same as IST. I mu, the mu current is same as the source current. Fine. So what you can do is, you can see that this mu will increase. If this mu is increasing, it means the diode D1 current is increasing and the diode D2 current is decreasing. Is it fine? So I mean, these conditions which we have analyzed here, you can use, you can implement these conditions using this circuit. In this circuit, you can treat this I mu and this as 5 ampere. So the resultant current in this diode in the upper direction is 5 minus I mu. You can see that as soon as this I mu is increasing, this current is decreasing, and if this I mu is increasing, then this IS current will also increase. Now this circuit will work. Now how to calculate this I mu and the overlapping interval? How to calculate that? To calculate that, we can apply the KVL here. So if you apply the KVL, now what will happen, guys? If you apply the KVL, please apply the KVL. So if you apply the KVL in this loop, it will be VST minus LS d I mu by dt is equal to 0. Fine. VST, the supply voltage minus this drop, equal to 0. I can write it like this. Many students write it in negative way. I mean, since you are going from minus to plus, so they will write minus VST plus I LS di mu by dt equal to 0. So I am following the opposite convention. Since I am going from minus to plus, it will be added, and then plus to minus, it will be subtracted. So VST minus LS di mu by dt is equal to 0. You can write it like this. Now, what is the VST? VST is 50 sine of omega t. 50 sine of omega t is equal to LS. LS is 0.5 di mu by dt. Okay, what you can do is take this 5 in the denominator and dt on this side. So it will be di mu by dt will be equal to, tell me guys, it will be 50 upon 0.5. 50 upon 0.5 is 100. 100 sine of omega t. Okay, take this dt on the other side. Take this dt on the other side. Okay, so it will become 100 sine of omega t into dt. Fine. Now what you can do is you can divide it with omega and multiply with omega. Omega is 10. Omega is given as 10. So it will be di mu is equal to, if you divide it with 10 and multiply with, then it will become 10 sine of omega t d omega t. Why I have written 10 here? Because divide by 10, multiply by 10. So divide by omega, multiply by omega. That omega multiplied by omega term I have written in d of dt. And divide by omega. Omega is 10, so cancel with this 100. So it will be 10 sine of omega t d omega t, you can write it. And take the integration on both sides. Take the integration on both sides. Now you can see that this I mu is changing from 0 to 5 ampere. 0 to 5 ampere. In what interval? Here the integration is with respect to omega t. 0 to mu. In mu radian, because it is with respect to radian, na? So in mu radian, this current has increased to 5 ampere. Now you can calculate 5 is equal to 10 into integration of sign is minus cos, upper limit minus lower limit 1 minus cos mu. Is it fine, guys? This way you can solve it. From here you can see that cos mu came out to be, what is cos mu? Cos mu will be equal to, I suppose it is half. You can take 10 in the denominator, so it will be half. Okay, so cos mu came out to be half. So mu came out to be 60 degree. Overlapping interval is 60 degree. Is it fine, guys? Overlapping interval is 60 degree. So we found that the overlapping interval is 60 degree, not 120, it's 60. It is 60, I suppose. Cos mu is half. Cos mu half means mu is equal to 60 degree. So we found the overlapping interval like this. It means this overlapping interval is up to 60 degree. So if I want to plot the wave shape, then this overlapping interval will be up to 60 degree. Let me plot this now. So this overlapping interval came out to be up to this instant. In this interval, this source current is increasing from 0 to 5. Okay, and the output voltage will remain 0. Okay, now the current has reached to 5 ampere. After this mu interval, you can see that the current has reached to 5 ampere and this current has reached to 0. So this diode will remain off. Now this diode will turn off. Okay, this diode will turn off. If the diode is turned off, then the entire current will flow through the inductor now, flow through the source now. So now from 0 to, from this mu to pi, you can see that the entire 5 ampere current will flow through the inductor. It means the source current will remain constant now. Now what will be the output voltage? So up to this interval, output voltage was 0 because both the diodes were conducting. Freewheeling diode was sorted. If the freewheeling diode was sorted, then the output voltage was 0. So during the overlapping interval, output voltage was 0. Now after mu, what will happen? After mu, this current has increased to 5 ampere and it is constant. If the inductor current is constant, then the voltage across the inductor will be 0. This voltage will be 0. So whatever the supply voltage is, the same will appear here. Same will appear here because there is no drop in the inductor, there is no drop in the diode because I am taking ideal diode. So you can see that now the output voltage will be same as the supply voltage. Okay, so after this point, the output voltage will be same as the supply voltage up to pi. Okay, up to pi, output voltage will be same as the supply voltage. Is it clear, guys? Up to pi, you can see that the output voltage will be same as the supply voltage. Fine. Now what will happen after pi? After pi, this voltage is becoming negative. Now tell me what will happen. If this voltage is becoming negative, after pi this diode has to conduct now. But since the inductor has 5 ampere, so you can't say that the inductor will change the current abruptly through 0. No, sir. Slowly the current will decrease. Slowly the current will decrease. Okay. Slowly the current will decrease. During this interval, again there is a overlapping. After pi there is again overlapping. Again this diode D1 and D2 will conduct and this current will decrease this time and this current will increase slowly. Okay. This current will decrease, this current will increase slowly. So you can see that this current will decrease and this current is increasing. So since the freewheeling diode is conducting, output voltage will remain 0 up to that. After this point, again after this point, entire current is shifted to the diode. So it means the output voltage will remain 0. Is it fine? That's why I am not interested in calculating this interval. This point is, let's say, pi plus whatever mu2 or mu1, whatever you write it. Okay. But I am not interested in calculating this interval. Why? Because during this pi to pi plus mu2, this diode and this diode both are conducting, so output voltage will remain 0. After this interval, what will happen? Entire current is shifted to D2, so again the output voltage will remain 0. Okay. That's why I am not interested in calculating this interval because output voltage remains 0 in the entire period. Now again at 2 pi, what will happen? Again the same thing will happen, which we have studied at 0. The same thing will happen at 2 pi. So again there will be a overlapping period. Okay, there will be overlapping period up to this 2 pi plus 60. Is it fine? And the current will increase like this up to 3 pi. I hope it is clear, guys. And the output voltage will remain 0 up to this point, and then this will be my output voltage. This is 2 pi plus mu. This is 2 pi plus mu. Is it fine? So we have calculated the output voltage. Is it clear, guys? Tell me. Tell me, everyone. So we have calculated the output voltage. Is it clear? Say yes or no. Tell me, everyone, is it clear? So we have calculated the output voltage wave shape. This is my output voltage wave shape. This is my output voltage wave shape. You can see that. Now the question is, what is the average value of this output voltage wave shape? The period is 2 pi. So 1 upon 2 pi, we need to take the area under one period. Area under one period is this area only, mu 2 pi. And the expression is Vm sin omega t. 50 sin omega t d omega t. Integration of sine is minus cos. Upper limit minus lower limit is 1 plus cos mu. Okay. Integration of sine is minus cos omega t. Upper limit minus lower limit will be this. Now you can put this cos mu value. You can put this cos mu. Cos mu is half. So you can put this value as half and you can calculate the average output voltage. Now the average output voltage will be less than the previous value. Because in previous case, the average output voltage was 50 upon pi. Now, because of this overlapping, you can see that the average value will decrease. This area has decreased. That's why the average value will decrease. Is it clear, guys? So this is the effect of the source inductance. I told you how to calculate this. How to calculate this. I don't remember any formula. So if you don't remember any formula, you can apply the KVL concept. Now, you should understand the concept. Using that concept, I have solved it. There are some teachers who take it linear variation. This will not be a linear variation. Let me tell you guys. The current will change like this. Current you need to do is in this expression, in this I mu, 0 to I mu, and here if you need the function, if you need the expression of the equation of this function, what you need to do is you put 0 to I mu t, and here you put 0 to omega t. Then you will get the relation of this I mu current. Okay, let me write it. Let me write it. Where I can write it? Okay, I can write it on the next screen. So you can write it like this: d I mu 0 to I mu is equal to, here you have 10 sine of omega t, 10 sine of omega t d omega t, and you can integrate this 10 sine omega t from 0 to omega t. Don't put 0 to mu here, you put 0 to omega t here, variable limit you should be there, you should put there, and 0 to I mu t here. Okay, now you can calculate this I mu as 10. Now you have minus cos of omega t, upper limit minus lower limit, 1 minus cos of omega t. This will be the expression for I mu t. So now you can see that, at omega t equal to 0 it is 0, and at omega t equal to mu, it will become cos mu. Cos mu is half, 1 minus half is half again, 10 into half is 5. So this current will reach to 5 ampere, and the wave is not linear. This wave is not linear. Okay, this wave is not linear, it is moving like this. Is it clear, guys? I hope it is clear. Okay, so this way you can check the equation of this part. So this will not be linear, because some teachers do it like this. They will make it linear, and then it is buffering again. Sorry from my side, guys. I don't know what's the problem with the internet. So internet is creating this problem. Okay, tell me, is it clear now? Okay, from where you have not understood that? Tell me, from where this created problem? Tell me, so that I can repeat that. I can repeat that. Tell me, guys, from where, from which point you want me to repeat? From which point you want me to repeat? Tell me. Have you understood how the current wave shape will look like? So to calculate this current variation, if you want to check this current variation, how the current is changing, if you want to check this current variation, what you can do is, in place of this equation, don't put this constant limit. Don't put this constant. Here the I mu, the limit is on I mu. Na? So what you do is, you need the function. If you need the function, don't put the constant limit. Put the variable limit from 0 to I mu. So put 0 to I mu, and here 0 to omega t. Don't put it 0 to mu interval. You are putting the fixed interval. That's why you are getting this equation. So you want the variable, you want the function, na? You want the function, na? So what you can do is, you can put the limit as 0 to omega t here and 0 to I mu t here. So you can calculate the I mu is equal to 10 into 1 minus cos omega t, and the wave shape will look like this. And you can check that at omega t equal to mu, this cos mu will become half. 1 minus half is half into 10, 5. So it will reach to 5. Okay, so you can check it like this. I hope it is clear. I hope it is clear. So this will be the wave shape of the current during this interval. It will not be linear. Remember this point. It will not be linear. Okay, it will not be linear. Is it fine, guys? Let's proceed. Sorry for the internet connection. I don't know why it is creating problem. Why it is creating problem? I don't know that. Okay, so let's proceed, guys. Let's proceed with the next topic. So I told you what is the effect of source inductance. So you can see that due to the source inductance, the average output voltage get reduced. Previously it was 50 upon pi. Now it is 50 upon 2 pi. 50 upon 2 pi into 1 plus cos mu. Now it is this. Now you can analyze that. This is correct. Why? Let's say there is no source inductance. If there is no source inductance, you can put the mu as 0. If mu is 0, it will become 2, and you can cancel the 2. Again you will get 50 upon pi answer. If there is no source inductance, it means the mu interval will be 0. If you put mu equal to 0 here, it will become 50 upon 2 pi into 2. That 2 will cancel, and you will get the same answer, 50 upon pi. It means this expression is correct. Okay, so you can check it like this also. I hope it is clear. Now let's move to the next thing, and next thing is, I am revising you the phase controlled rectifier now. Okay, let's revise the phase controlled rectifier. Okay, so I have taken the L load first, and These are Vt and okay. So please try to draw the wave shape. Let's see how many of you can draw the wave shape. How many of you can draw the wave shape? Take the firing angle as 45 degree and 90 degree. Okay. Let's take two firing angle. Alpha equal to 45 and 90 degree and draw the wave shape. Please do it. Till then I can add some more slides. I can add some more slides. Okay, wait, let me add some more slides here. Okay, so that it is easy for me. Then till then you can solve this question. No? Till then you can solve this question. Let me add some slide. Okay, I think I have added enough. It's enough now. Okay, that's perfect. So let's come back to the original slide. Okay, this was the question. Now try to solve this question, guys. Try to solve this question. Do it fast. Is it still buffering? I don't know why it is creating problem with me. Anyway, let's look at this problem, guys. Now we have the inductor. Okay, and alpha, let's take alpha as 45 degree. Let's take alpha as 45 degree. Okay, so if I take alpha as 45 degree, then what will be the wave shape? Let's assume that this is 0 and this is my VST. Since previously no thyristor was conducting, so there was no current, there was no output voltage. This output voltage was 0 and there was no current, I know T. This current was also 0. Okay, so you can see that if there was no current, this output voltage was 0 up to this instant alpha. Let's call it alpha instant. So up to this instant alpha, let me take this down. Up to this instant alpha, there was no current, so there was no voltage. Okay, so you can see that the output voltage was 0. The output voltage was 0 and the output current was also 0. There was no current. And the thyristor voltage, on this side you have 0 voltage because there was no current, so there was no drop. So if you have assumed that lower point is at 0 volt, the upper point will also be at 0 volt since there is no drop now. So if this is 0, this will also be 0. Now tell me the voltage across the thyristor T. The voltage across the thyristor is same as the supply voltage VST because this side minus this side I have to take. So this voltage has to be VST. It means Vt has to be VST. Okay, this will be, it's same as the supply voltage. Okay, so Vt voltage across the thyristor is positive. This side voltage minus this side voltage is positive. It means this thyristor is under forward blocking mode. This thyristor is under forward blocking mode. Now if this thyristor is under forward blocking mode, you can fire it at some angle alpha. So I have fired it at some angle alpha. Alpha can be taken as 45 degree or 90, whatever. Okay, now what will happen, guys? Now from this alpha onward, the current will start. The thyristor will get fired and the output voltage will be same as the supply voltage because it will be connected in parallel. So output voltage will be same as the supply voltage and current will start. So if the output voltage is same as the supply, so up to pi, let's plot up to pi first. Let's plot up to pi. So up to pi, the output voltage will be same as the supply voltage. It means the output voltage will look like this. It will be same as the supply voltage. Okay, up to this instant pi. This instant is pi. But what will happen after pi? We'll see that. We'll see that. So up to pi, the output voltage will be same as the supply voltage, and since the voltage across the inductor is positive, up to pi, the voltage across the inductor is positive, the current will rise. The current will rise, and it will reach to the maximum at this point. Why it will be maximum at this point? Because the voltage has become zero. Whenever the voltage across the inductor becomes zero, whenever this voltage is zero, what does it mean? It means the current has the maxima or the minima. There are three situations now. Whenever this voltage becomes zero, either you have the maxima of the current, or you have minima of the current, or you have constant current, okay? But since previously current was increasing and this voltage has become zero for some instant, maybe for minute instant, it came out to be, this value become zero, so the current will reach at the maxima point. It will not be minima because the current is rising, because the voltage is positive, so dt will be positive. If dit by dt is positive, current will rise. Now at this instant, the voltage becomes zero for some instant, for just 0 instant. So current will reach to the maxima point at this point. Now what will happen? Since the current has developed, after pi, this voltage become negative. This thyristor cannot turn off. Why? Why the thyristor cannot turn off? Tell me. Why this thyristor cannot turn off? This thyristor cannot turn off because inductor has some current. Whenever the load is inductive, remember, whenever the load is inductive, remember this point, that this thyristor, once this circuit start working, the thyristor will turn off only if this current has become zero. Otherwise, this inductor will not let this thyristor to turn off. Because in inductor, current cannot change abruptly. So if the thyristor will turn off at this point, then current has to become zero abruptly. But the current cannot become zero abruptly in case of inductor. So what will happen, guys? After this point, this inductor will keep this thyristor turn on. If the thyristor is turn on, even if the voltage is negative, if the thyristor is conducting, then the output voltage will remain as the supply voltage, because it is sorted. So the output voltage will be same as the supply voltage. It means the output voltage will now become negative. It will become negative, okay? Now up to what instant this will conduct? The instant by which this current becomes zero, up to which this current becomes zero. Let's say at this instant the current becomes zero. At this instant the current becomes zero. Up to this instant, the voltage will be there. It means the thyristor will conduct. The thyristor will conduct up to this instant. Now why the current is decreasing now? Can you tell me why the current is decreasing now? Because the voltage across the inductor is negative. This VLT is negative. That's why the current. If the current becomes zero, then at this instant the thyristor will turn off, since this voltage is still negative. So at this instant the thyristor will turn off and the output voltage will become zero, because there is no current now. So the output voltage will become zero up to 2 pi plus alpha. Up to this 2 pi plus alpha. Up to this 2 pi plus alpha, output voltage will remain zero and the current will also remain zero. Okay, so it started from alpha and now this point is 2 pi. This point is 2 pi plus alpha. Okay, so up to 2 pi plus alpha, the current will remain zero and the voltage will also remain at zero. Is it fine, guys? This is 2 pi plus alpha. Now at 2 pi plus alpha, again you fired T1. So the voltage will look like this. Okay, so the voltage will look like this. I hope it is clear. And the current will rise again. It will reach to the maximum value and then it will reach to the zero value. Okay, so this will be the wave shape of the current. It stopped working now. Is it clear now? Tell me. Is it clear? So without calculating anything, you can plot the wave shape. Now you will ask me, sir, how you have plotted these wave shape? What should be the idea? Okay, let me tell you the basic point about the inductor. What should be the basic point about, let me tell you the basic point about the inductor so that you can plot the wave shape without any calculation. Okay, let's say you have an inductor. Let's say you have an inductor. In inductor, remember there are 2-3 important points. What are those points? First of all, we know that in inductor L di by dt is the voltage across the inductor, VLT. Okay, L di by dt is equal to VLT. We know that. If this VLT is positive, if VLT is positive, if this voltage across the inductor is positive, it means L di by dt is positive. It means L di by dt is positive. What does it mean? It means this di by dt is positive. Di by dt is positive. What does it mean? It means this IT will be rising. IT will be rising. IT will be rising. Okay? IT will be rising. Now, if VLT is negative, then what will happen? It means L di by dt is negative. It means di by dt is negative. It means IT will fall. IT will be decreasing. IT will be decreasing. Remember this point. Now the third point. The third point is, if VLT is 0, if VLT is 0, if the voltage across the inductor is 0, then L di by dt is 0. It means di by dt is 0. Now di by dt will be 0 in 3 cases. There will be 3 cases. Either you have the maxima, either you have maxima of the current, or you have the minima of the current. Either you have the maxima of the current, or you have the minima of the current, or the current is constant, or the current is constant. Then you will have di by dt equal to 0. Okay, so there will be 3 possible cases. There is one more case, and one more case is I itself is 0. I itself is 0. Then also di by dt will be 0. If I is remain at 0, I is remaining at 0, then you will say that di by dt will become 0. Okay, so there is one more case, but I am not considering that. But anyway, so there will be 3 cases now whenever this VLT is 0. Now there is one more point, and that point is very important. This point is very important. Let's say you have inductor. In inductor, let's say the current shape is, let's say we have a circuit, and here are some sources I have connected. Okay, there are some sources. We don't know about these sources. There are some sources, and we have an inductor load as load. We have an inductor as load. Okay, and let's say the current is like this. This is the current in the inductor. Okay, let's say this is the current in the inductor. Let me redraw this current. So now I have an inductor, and let's say the current in the inductor is IT. So I am plotting this ILT. Let's call it ILT. So now the current is, let's say the current is like this. Okay, this is the current in the inductor. The wave shape of the current is provided to us. Now let's analyze the points. There are some special points about the inductor. What are those special points? Let me tell you. Please be careful, guys. Look at this point. At this point, the height is, let's say, I naught. At this point, the height is I naught. At this point also, the height is I naught. Let's call it 0 point. Let's call it alpha point or alpha 1. This point is alpha 1. Okay. I call this point as alpha 1. This point is alpha 1. Is it fine? Now, the same current is repeating. So, up to this instant, if you take VLT dt, if you calculate the area of the voltage across this inductor from 0 to alpha 1, since the current is repeating at the same instant, I mean the current is repeating at alpha 1. Whatever the current at 0, the same current will come at alpha 1. So if you are calculating VLT area from 0 to alpha 1, this has to be 0. This has to be 0. Look at this point. Let's call it alpha 2. This point is alpha 2. Okay, this point is alpha 2, and let's call this point as alpha 3. Okay, this point is as alpha 3, this point is alpha 2. Again, you can see that at alpha 2 current is 0, and at alpha 3 current is again 0. So what you can say is, you can say that from alpha 1 to alpha 2, VLT dt will again be 0. Between 2 points, if current is repeating, so between those 2 points in which the current remains the same, let's say at alpha 2 and alpha 3, the current is same, current is repeating. Here it was 0, here also it is 0. So the area of the voltage VLT will be 0 between these 2 points. Now let's come to this point. Let's say this point is alpha 8. Let's say this point is alpha 8. Now tell me, if this point is alpha 8, can you calculate the area between alpha 1 and alpha 8, or 0 to alpha 8? What will be this area? Can you tell me? 0 to alpha 8. What is VLT? Can you tell me, guys? What is VLT? Tell me, guys, what is VLT? From 0 to alpha 8, what is VLT? At t equal to 0, the current is I naught. At alpha 8, the current is again I naught. Okay, now tell me, what is the area of the VLT? What is the area of the VLT? Can you calculate that? Can you tell me that? Tell me, guys. Tell me, everyone. Tell me, everyone. Yes, this area will be 0 again. This area will be 0 again. It means you can write it in a reverse way. You can say it in a reverse way. If we have an inductor, and let's say up to from some time t1 to t2, from some time t1 to t2, if VLT came out to be 0, VLT area came out to be 0, if VLT came out to be 0 between time t1 and t2, then you can say that IT1 must be equal to IT2. Is it clear, guys? Have you understood it? I can say it like this. In inductor, remember this point. In inductor, remember this point. In inductor, remember this point. This is again very important, very powerful point. Okay, it is very powerful point. So you can see that I1t will repeat its value. If between time t1 and t2 this area is 0, or in converse way you can say that if VLT is 0 between time t1 and t2, then the current value at time t1 and the current value at time t2 has to be equal. Is it clear, guys? Will you understand? Will you remember that? Will you remember that? Whenever you have the same current now, let's say at this point and this point you have the same value of the current. So between this point and this interval, if you want to calculate the area, that area will be 0. Okay, that area will be 0. And converse also true. If the area of the VLT is 0 between some time t1 and t2, then you can say that at time t1 and at time t2 the current value will have the same magnitude. Okay, I hope it is clear. Can I proceed, guys? Now let me tell you one more point. So this is point number 4. This is very important. Now let's come to point number 5. Let's come to point number 5 in inductor. And that point number 5 is, let's say you are standing at alpha 3 and there is a point we call alpha 4. This point, let's say alpha 4. This point is alpha 3. Okay. Now, if you look at this alpha 3 and alpha 4, you can see that at alpha 3 the current is 0 and alpha 4 the current is negative. Okay. At alpha 3 the current is 0 and alpha 4 the current is negative. What does it mean? If you want to calculate from alpha 3 to alpha 4 of VLT, it will be negative. Why it will be negative? Because it's not repeating. It's not repeating. It has decreased. The current value has decreased to some new value. From alpha 3 to alpha 4, current has decreased. Current has decreased. Again, it's buffering. Tell me guys, is it clear now? Internet is creating problem. I don't know why. Okay, thank you. So I told you from alpha 3 to alpha 4. If you look at the current at alpha 3, it is 0. At alpha 4, it is negative. So if you want to calculate the area of VLT from alpha 3 to alpha 4, it will be negative because the current has decreased. Now, can you tell me from alpha 3 to alpha 8, will it be positive or negative or 0? Tell me guys, what is this area? From alpha 3 to alpha 8. From alpha 3 to alpha 8, tell me, will it be positive, negative or 0? Tell me guys. VLT, area of VLT. Tell me, will it be positive, negative or 0? Tell me guys, from alpha 3 to alpha 8. From alpha 3 to alpha 8. Tell me guys, what is the area? Area of VLT. The current is positive. So you can say that the current has increased. That's why this will become positive. I hope these points will be clear to everyone. I hope these points are clear. Now, if these points are clear, then we can come back to this problem. Now you can see that the conduction start at alpha. From alpha to pi, the voltage across the inductor is positive. Voltage across the inductor is same as the supply voltage. So it is positive. From alpha to pi, it is positive. That's why the current is increasing. And current has increased to this value. We know that now the thyristor will not off because the current has developed some value. Inductor has developed some value. Since the inductor has developed some value, it will not let the thyristor turn off. Okay. So it means the thyristor will not get turned off. Thyristor will still conduct. If the thyristor is still conducting, then the output voltage will remain as same as the supply voltage. And since the supply voltage is negative, so the output voltage will also go negative. If the output voltage is also going negative, then the current will start decreasing. Now at this instant, the current has become 0. At this instant, the current is repeating. Now tell me, at this instant, whatever the current at alpha was, the same current is repeating here. It means this area has to be 0. This area has to be 0. Tell me guys, is it clear or not? This area has to be 0. Tell me everyone, this area has to be 0. Because the current is repeating the same value now. That's why this area has to be 0. And this area will be 0 only if, what is this length? This length is pi minus alpha. So this length has to be pi minus alpha because it's a symmetric wave. Whatever the positive area is, the negative area should be equal. Whatever the positive area is, the negative area should be equal. It means then only the total area will become 0 now. So if this length is pi minus alpha, this length should also be pi minus alpha. So what about this instant? Can you tell me about this instant? This instant is pi and this length is pi minus alpha. So this instant will be 2 pi minus alpha. Is it clear guys? This point, what about this point? This point is 2 pi minus alpha. This point is alpha, this point is 2 pi minus alpha. Is it clear guys? Tell me, say yes or no. This point is 2 pi minus alpha. How much time this thyristor will conduct? And tell me guys. Okay, can you wait for maybe 4 or 5 minutes so that I can correct it? Can you wait for 4 or 5 minutes so that I can correct this internet issue? Because I have to restart the modem. I have to restart. Is it fine now? Tell me everyone. Is it fine now? Okay, okay. Thank you. Thank you, thank you. Thank you for your patience, guys. I hope it will not create any problem now. But still I'm not sure. Okay. Okay, let's continue the class. Let's continue the class. So I told you that that this area will be equal to this area. Why? Because this current is repeating. Because the current is repeating. Okay. Okay. Because the current value is repeating. Since the current value is repeating, that's why this area, the positive area, has to be equal to the negative area. Okay. So if this length is and this positive area will be equal to negative area only if this is symmetric. I mean the wave is symmetric now. Only if this length is equal to this length, and this length is pi minus alpha. So this length has to be pi minus alpha. Okay. This length has to be pi minus alpha. So what about the total length? If this is alpha, this is pi, and this length is pi minus alpha. So you can calculate this instant. This instant is 2 pi minus alpha, and you can calculate the total length. Total length came out to be 2 pi minus alpha minus alpha. That is 2 pi minus 2 alpha. Is it clear, guys? So the conduction time of the thyristor, conduction time of the thyristor will be equal to, tell me guys, this is 2 pi minus alpha minus alpha. So it will be 2 pi minus 2 alpha. This will be the conduction time of the thyristor. Is it clear, guys? So we have calculated the conduction time of the thyristor, and I told you the properties of the inductor, how the inductor will behave. That's how I have plotted these waves without any calculation. Without any calculation, I can plot these waves. Okay. So you can do the same. You can do the same. Just remember these points. These points are important. Okay. I hope it is clear. Now, what will be the Vt? You know that from alpha to this instant, thyristor is conducting. If thyristor is conducting, it is sorted. It means the voltage across the thyristor will be 0. The voltage across the thyristor will be 0. Fine. The voltage across the thyristor will be 0. Now, after this instant, after this 2 pi minus alpha, what will happen? After this 2 pi minus alpha, the thyristor will turn off. It is open now. If it is open, then the output voltage is 0 and this side voltage is VST. Now, what is this Vt? Vt is this side voltage minus this side voltage. It means VST minus 0. Now, Vt will become same as supply voltage. So, at 2 pi minus alpha, the supply voltage is negative, and it will be positive like that. Okay, it will go like this, and then again at 2 pi plus alpha we have fired it. So you can see that at this 2 pi minus alpha to 2 pi, the thyristor will remain reverse biased. From 2 pi to 2 pi plus alpha, from 2 pi to 2 pi plus alpha, it will become under forward blocking mode. Now what is the circuit turn of time for thyristor T1? The circuit turn of time for thyristor T is this negative reverse bias region. What is this time? This time is 2 pi minus 2 pi minus alpha. It is alpha. So the circuit turn of time for the thyristor is alpha. Tc. Tc is alpha by omega. Okay. So the circuit turn of time for the thyristor is alpha by omega. I hope it is clear to everyone. So now you can plot it. Take alpha as 45 or 90, whatever you want to take, you can take it. Okay. So I have plotted the wave shape of VLT, voltage wave shape, and the current wave shape. What is the average output voltage? Tell me, guys. V naught T average. V naught T average will be 0. Whenever, let me write one more point in inductor. Whenever current is periodic, whenever this ILT is periodic, whenever ILT is periodic, if ILT is periodic, VLT average will be 0. The average voltage across inductor will be 0, and vice versa. And vice versa. I'm not telling you why this is true, because it's not the right time anyway. But remember this point: whenever ILT, whenever the inductor current is periodic, the voltage across the inductor has 0 average value. VLT average will be 0. Okay, just remember this point. Whenever ILT is periodic, then VLT average voltage will be 0, and vice versa. If VLT average is 0, current has to be periodic. Now you can see that. In this question, since the current is periodic, it will be periodic. That's why the average voltage will be 0. You can see that the area under one period is always 0. So if area under one period is always 0, then the average will also be 0. Okay. I hope it is clear to everyone. Now let's move to the next shape. Now we have this circuit. Tell me guys, we have this thyristor and there is a diode, freewheeling diode, and we have a pure inductor. Now let's see what the wave shape of V0 and I0. This is my V0, okay, this voltage is V0 and this current is I0. This current is I0. We need to plot the wave shape of V0 and I0. How to plot it? It's very simple. And there is a thyristor. The firing angle of the thyristor is, let's say, alpha. We are firing the thyristor at an angle alpha, okay. So let me draw the wave shape. This is alpha. Let's see what will happen. Let's say initially nobody was conducting. Nobody was conducting, and let's assume that this is 0. So if no one was conducting, no diode or thyristor was conducting. So what will happen, guys? If I have assumed that this is 0, this voltage will also be 0. Tell me guys, this will also be 0 because there is no current in the inductor. There is no current in the inductor, so there is no voltage across the inductor. So if this voltage is 0, this voltage will also be 0. Okay, so this side is 0. Output voltage is 0 up to this point. Output voltage is 0 up to this point. Alpha. Up to alpha point, output voltage will be 0 and there was no current. There was no current, okay. The current was again 0. This I0 current was again 0. Now at alpha, this side voltage is 0. Before alpha, this side voltage is 0 and this side voltage is VST, and we know that VST is positive. VST is positive and this side is 0. So this thyristor voltage is positive. This side voltage is higher than this side. So it means the thyristor was under forward blocking mode. So from 0 to alpha, you can see that the thyristor is under forward blocking mode because this VT is positive. This side is higher than this side. So you can fire it. Since it is under forward blocking mode, now you can fire the thyristor. Let's say I fire the thyristor. If I fire the thyristor, it will be sorted. If it is sorted, then the output voltage will be same as the supply voltage VST. Okay. So from this alpha to pi, let's look at this interval only, alpha to pi. From alpha to pi, output voltage will be same as the supply voltage. Tell me, is it correct? From alpha to pi, this instant is pi. Now tell me, if the output voltage is same as the supply voltage from alpha to pi, then what will be the current? The voltage across the inductor is positive, you can see that. So the current will rise and it will reach to the maximum. I don't want the equation. I don't want the equation. Just write the wave. So the wave will look like this. Up to this instant, the current will go and it will reach to the maximum at this point. So current has developed now. Now what will happen? Tell me guys. From this pi onwards, can this thyristor be conducting? Tell me. From this pi onward, will this thyristor still conducting? No. Why? Because there is a freewheeling diode. There is a freewheeling diode. Whenever the freewheeling diode is there, remember, output voltage can never be negative. In the previous case, output voltage goes negative. But now in this case, output voltage will never go negative. Why? Because of the freewheeling diode. Let me tell you one more reason. Let's say if thyristor is conducting after pi ohms. After pi, let's say the thyristor is still conducting. If the thyristor is still conducting after pi, then it will be sorted. Thyristor will be sorted. Tell me guys. Then the thyristor will be sorted. If the thyristor is still conducting after pi, then the thyristor will be sorted. It means this point has to be equal to VST. It is sorted. If it is sorted, then this voltage and this voltage has to be equal. This voltage is same as the supply voltage, and supply voltage is negative. After pi, the supply voltage is negative. It means the output voltage has to be negative. And this side is 0. Now tell me, if this side is negative and this side is 0, then this diode will forward bias. This diode will get forward biased. If diode will get forward biased, the voltage across inductor will become 0 and the entire current will flow through this. Is it fine? That's why I am telling you that freewheeling diode will turn off. Okay, because this inductor needs the path. Inductor current needs the path. If there was no freewheeling diode, then what will happen? This current has to flow through the thyristor. There is no other path. That's why in the previous question, this has to conduct. But now in this situation, there is an alternative path. Current can flow via this path. Okay. That's why after pi, what will happen is freewheeling diode will conduct and the output voltage will become 0. Output voltage will become 0 and freewheeling diode will conduct. Since the output voltage across the inductor is 0, now tell me, if output voltage is 0, then the current will remain constant. Okay, the current will remain constant. So current will remain constant up to this 2 pi plus alpha. This is 2 pi and this is 2 pi plus alpha. Up to 2 pi plus alpha, the freewheeling diode will conduct and the output voltage will remain 0. Now at 2 pi plus alpha, what will happen, guys? Now at 2 pi plus alpha, again this thyristor will get fired, because the thyristor will turn off at this point. At pi point, thyristor will turn off. Okay, at the pi point, thyristor will get turned off and the freewheeling diode is conducting. Now it will be fired again at 2 pi plus alpha. At 2 pi plus alpha, it will be fired again. If it is fired again, then the output voltage will look like this. Okay, this is 2 pi plus alpha and this point is 3 pi. Okay, this point is 3 pi. So the output voltage will still be positive. Now the current will again rise. Current will rise again because the inductor voltage is positive. It means the current will rise again. And then from 3 pi to 4 pi plus alpha, output voltage will remain 0 and the current will remain constant. And then again, it will be positive. So current will rise again. Okay. So current will keep on rising. You can see that. Is it working now? Tell me, guys, is it working now? Is it working now? Okay, now it's okay. Okay, so I was telling you. Okay, thank you. Sorry for the disturbance, guys. I don't know what's happening. I don't know, because the internet is creating problem. I don't know why it is stopping again and again, because the speed is fluctuating. I don't know why it is happening. Maybe. Okay, so I told you that in this case, what will happen is the current will keep on rising. The current will keep on rising like this. Okay, and you can see that the current is not periodic. If the current is not periodic, average voltage will not be 0. You can see that the average is not 0, average is positive. Okay, I hope it is clear to everyone. So be careful, guys. This is again a very important case. These two cases are very important. Here you have a thyristor with the inductor, and here you have one more freewheeling diode. Okay, now let's proceed. Now I have this RL circuit. In this RL circuit, what will happen, guys? Tell me. In this RL circuit, what will happen? Tell me. At alpha, you are firing the thyristor. Let's say at alpha you are firing the thyristor. Let's take this instant as alpha. So at alpha you are firing the thyristor. As soon as you fire the thyristor, the current will start from 0 value itself because of the inductor. It's an AC transient case. You can see that this is my AC transient case. In AC transient case, you know the current equation. So the current equation will be the steady state current plus the transient current. I told you that we are going to use this equation. Let me revise. Let me tell you where I have told you. Yes, I told you about the transient, AC transient. Now you can remember that RL circuit is there and we have AC supply. RL circuit is there and we have the AC supply. So we have the transient current. But now the problem is we are firing at an angle alpha. Let me show you that. Yes, we are firing at some angle alpha. So what will be the current? The current will be, the steady state current will be Vm by Z sine of omega t minus theta Z. Theta Z is the impedance angle, R plus J omega angle. This will be my steady state angle, a steady state current. Now there is one more transient current. Now what is the transient current? The transient current will be at omega t equal to alpha, because you are firing this at omega t equal to alpha. At omega t equal to alpha, this is not 0. What is the value of this current? It is Vm by Z sine of alpha minus theta Z. To make it 0, you have to apply, the transient current has to be negative of this value, sine of alpha minus theta Z. Okay. The transient current has to be negative of this value. Whatever the value of this steady state current at omega t equal to alpha, because you are firing at alpha now, you are switching on at angle alpha. So at an angle alpha, the steady state current is Vm by Z sine of alpha minus theta Z. So the negative of that current will be the transient current to make it 0. Okay, and it will decay e to the power minus R by omega L, omega t minus alpha. Okay, this will be the current equation. It means the current will start from the 0, current will start from 0, and the output voltage will be same as the supply voltage. The output voltage will be same as the supply voltage. Okay, so the output voltage will be same as the supply voltage up to pi at least. Let's first look at up to pi, then we'll look after pi. So up to pi, you can see that the output voltage will be same as the supply voltage. Okay, from alpha, this is pi. From alpha to pi, output voltage will be same as the supply voltage. Fine. And the current will go like this. Current will start from 0 and will go like this. Current will go like this because the current has sinusoidal component and the exponential component. That's why the current will start from 0 and it will go like this. And at this pi instant, you can see that the current is not 0. Current is not 0. Since the current is not 0, the thyristor has to conduct because there is an inductor. In inductor, the current has developed some value. If the current has developed some value, it will force this thyristor to conduct. It means this thyristor has to conduct. Up to what instant? Up to the instant at which this current becomes 0. Let's call this instant as beta. So up to beta, this thyristor has to conduct, and if the thyristor is conducting, the output voltage will be same as the supply voltage, and output voltage you can see that it's negative, so the supply voltage will also be negative up to beta. At this beta instant, what will happen? At this beta instant, the thyristor will turn off. Okay, and then after that, thyristor will remain turn off up to 2 pi plus alpha. Current will also 0, voltage will also remain 0. Okay, this is 2 pi. This point is 2 pi. And this point is 2 pi plus alpha. So you can say that now up to 2 pi plus alpha, output voltage will remain 0 and the current will also remain 0. Current will also remain 0 and the voltage will also remain 0 because there is no current, there is no voltage. Now again at 2 pi plus alpha, we have fired thyristor T1. So the same shape will repeat. The same wave shape will repeat. Okay, and the current will go like this. Okay, is it fine, guys? So this way you can plot the current, I note current. You can plot the I note current and the output voltage wave shape. Now the question is, in this situation you can see that the current is periodic. The current is periodic. If the current is periodic, then the voltage across the inductor, VLT average, will be 0. VLT average will be 0. Since the current through the inductor is periodic, whenever you have discontinuous conduction, remember this point, guys. Remember this point. In any type of circuit, if the supply is periodic and the current is discontinuous, if the current is discontinuous, in discontinuous conduction, I naught T will be periodic. I naught T will be periodic always. Just remember this. Whenever the current is discontinuous, it will be periodic always. But the supply has to be periodic. Okay, supply side, this has to be periodic. Then only this will true. So if current is discontinuous, it means the discontinuous conduction is there. I naught has to be periodic. There is one more point. If the load contain R, then I naught T can never be rising, can never be increasing. Then also I naught T will be periodic. Whether it will be continuous or discontinuous, it doesn't matter. If R is there in the load, if load contain the resistance R, then I naught T will also be periodic. Then also, now you can see that this R is there. If R is there, it doesn't matter whether the conduction is continuous or discontinuous, whether the current is continuous or discontinuous. If R is there in the load, current has to be periodic. Okay, current has to be periodic. Now you can see that the current is periodic. If the current is periodic, then the average voltage across the inductor will be 0. Tell me guys. Now whatever the output average voltage is, whatever the total output average voltage is, we know that output average voltage is equal to VRT average plus VLT average, because in output you have two elements. Tell me guys, you can write it like this. Output average voltage will be equal to VRT average plus VLT average, but we know that since the current is periodic, so VLT average is 0, so whatever the output average is, that must be equal to R VRT average. It means this voltage average value. Okay. Now what is VRT average? VRT average is equal to R into IT average. R into I naught T average. This is equal to V naught T average. Now what you can do is you can take this R in the denominator and you can calculate the I naught T average value. Is it clear guys? So from here you can calculate the current average value. So the current average value is I naught T average is equal to V naught T average upon R. V naught T average upon R. This way you can calculate the current average value. Is it fine guys? Okay. Now there are one more point. There are some important points also. We know the wave shape of I naught T. This is the wave shape of I naught T. Now what is the wave shape of VRT? What is the wave shape of VRT? We know that VRT is equal to R into I naught T. R into I naught T. Okay, VRT is equal to R into I naught T. It means the wave shape of VRT and I naught T will remain same. I mean the wave shape will remain similar, shape will remain same. Only the amplitude will change because it is multiplied with R, na? So you can say that the voltage across resistance, the wave shape of the voltage across the resistance and the wave shape of I naught T will remain same. Now what is this inductor voltage VLT? How to calculate this VLT? We know that VLT is equal to whatever the shape of V naught T, subtract VRT from it. Okay, you will get the VLT. Now let's try to plot the VLT here. How to plot VLT? How to plot VLT? This is my V naught T, subtract VRT from it. What is the wave shape of VRT? VRT is similar to this. So let me plot the VRT. So VRT shape is like this. This is my VRT guys. Okay, I have plotted VRT like this. This is VRT. And this yellow color is V naught T. So V naught T minus VRT is VLT. So if you look at the VLT, let me use a white color. If you look at the VLT, from this point to this point, you can see that V naught is greater than VR. If V naught is greater than VR, then VLT is positive. VLT is positive. It means from this point to this point, this is my VLT and it is positive. This difference is positive. That's why up to this instant, the current is rising. You can see that up to this instant, the current is rising, and at this instant, VLT is 0. At this instant, VLT is 0. At this instant, VLT is 0. Why it is 0? Tell me guys. At this instant, VLT is 0. VLT is 0 at this instant, because at this instant, whatever the V naught T is, the same as VRT. V naught T and VRT are same. And I told you that VLT is V naught minus VR. So since they are same, they have the same value, that's why VLT is 0 at this instant. So at this instant, current has the maxima point. Okay? At this instant, the current has the maxima point. Now what will happen after that? After that, you can see that V naught T is less than VRT. So VLT is negative. During this interval, VLT is negative. You can see that. Since VLT is negative, that's why the current is decreasing. Now tell me, across this inductor, this is the current shape. Current started from 0 and it returned to 0 value again. Now tell me, what does it mean? Current started from 0 and it returned to 0. What does it mean? It means the VLT area. If you calculate the VLT dt, area of VLT dt from alpha to beta, what will be this area? Tell me guys. What will be this area? Tell me. The current is starting with 0 and it ends at 0 at beta. Now tell me, this current is the inductor current. This current is the inductor current. Now if you want to calculate this area VLT from alpha to beta, since the current is repeating, it has to be 0. It has to be 0. It means whatever this positive area is, this white color represent the VLT, na? Whatever this positive area is, the same will be the negative area. Is it fine, guys? The same will be the negative area. So remember this point. I hope it is clear. I told you how to draw the wave shape in RL circuit. In RL circuit, how to draw the wave shape. Now the question is, how to calculate this beta? You can't calculate beta. How to calculate this? The beta can be calculated by putting this current equal to 0. You put omega t equal to beta here and put it equal to 0, because we know that the current equation, in the current equation, at beta the current is becoming 0. If at beta the current is becoming 0, what will happen, guys? You can put beta in this equation, you can put omega t equal to beta and put it equal to 0 and calculate the beta. So it's not easy to calculate beta. Let's put the value of omega t equal to beta and put it equal to 0. So if you put omega t equal to beta here, then it will become beta and it will also become beta. Okay, so it will be beta and it will be beta. Now you can see that beta is in exponential term and beta is in sinusoidal term. You can't solve it. This is the problem. So beta can be, I mean, you can solve it using computer, but you cannot calculate it. This is a non-linear equation. You have to apply Newton-Raphson method. Okay, now what you need to do is, we need to calculate the average output voltage. How to calculate the average output voltage, guys? How to calculate the average output voltage? We know that this is the wave shape of the output, yellow color. This is the wave shape of the output voltage. What is the period? Period is 2 pi. This alpha point is repeating at 2 pi plus alpha. So the period of the output voltage is 2 pi. So now how to calculate the average output voltage? The average output voltage will be equal to V naught T average will be equal to area under one period divided by the time period. Time period is 2 pi. Okay, time period is 2 pi. I am taking from this point to this point. From alpha to 2 pi plus alpha, this is one period. Okay, this is one period. In this period, the area will lie from alpha to beta only. Area will exist from alpha to beta only. So what you can do is, you can take the integration from alpha to beta. And what is the wave shape of this equation? Wave shape is Vm sin omega t d omega t. Okay, this will be my average value of the output voltage. So the average output voltage will be Vm upon 2 pi, and if you integrate it sine integration will be minus cos upper limit minus lower limit, so it will be cos alpha minus cos beta. Okay, this will be my V naught T average. Whatever this V naught T average is, that must be equal to R into I naught T average. So from here you can calculate I naught T average also. Okay, from here why R into I naught T average? Because VLT average is 0. So the total average output voltage will be equal to R into I naught T average. So we have calculated the average output voltage, that must be equal to R into I naught T average. From here you can calculate the average output current. It's easy peasy. Let's move to the next case. In the next case we have freewheeling diode. Now in freewheeling diode case, what will happen? This voltage will never go negative. Whenever you have freewheeling diode, voltage will never go negative. Now how to draw the voltage wave shape? How to draw the voltage wave shape? Firing angle is alpha again. So let's draw the voltage wave shape. Let's take that this is firing angle alpha. Okay, if this is the firing angle alpha, take it down. Okay, this is my alpha. Now at this instant alpha, the output voltage will start up to pi at least. You will understand after pi what will happen. We'll look at this. But up to pi, the output voltage will be same as the supply voltage. It means the output voltage will go like this. Up to pi, the output voltage will be same as the supply voltage. Fine. The output voltage V naught T will be same as the supply voltage. This is VST. VST is Vm sin omega t. So the output voltage will be same as the supply voltage. From alpha to pi, this will be my output voltage. Now what about the current? The current will go like this. It's similar to the previous situation. It's similar to the previous case. Okay. So the current will go like this. It's not a pure sine wave. It has exponential term also. No? I have told you how to write the current equation. Okay. So from 0 to pi, the current will look like this. Now what will happen after pi? After pi, whatever the current has built up in the inductor, this freewheeling diode will provide the alternate path and this has to turn off. So after pi, the thyristor will turn off, and up to 2 pi plus alpha, thyristor will remain turn off. So up to 2 pi plus theta, this current will decay. This current will decay via exponential relation. Now whatever this current is, this will act as an initial current, and it will decay like this. Let me tell you guys, this current will not reach to zero value, because in exponential, whenever something is decaying exponentially, it requires infinite time to become zero. It requires infinite time to become zero. So it will be some positive value at this instant. At this 2 pi plus alpha, it has some positive value, and up to this instant output voltage will remain zero. Now what will happen? At 2 pi plus alpha, you have fired it again. So if you have fired it again, output voltage will again become like this. Output voltage will again become like this. Is it fine? The output voltage will become like this. Tell me everyone, is it clear or not? Output voltage will become like this. This is 2 pi plus alpha, and this point is 3 pi. Fine? This is 2 pi plus alpha, this is 3 pi. So now you can see that the current will rise again, but now the current is not starting from zero. The current will start from some positive value, So current will start from this positive value and will start increasing like this. So it has reached to some new value. And then again from 3 pi to again 4 pi plus alpha, up to 4 pi plus alpha, output voltage again remains zero, and the current will decay exponentially via this circuit, via freewheeling diode. The current will decay exponentially, but then it will reach to some new positive value. So after each cycle, you can see that since in the first cycle it was starting from zero, after the end of the first cycle it has some positive value, after the end of the next cycle it has some more positive value, after the end of next cycle it will have some more positive value. So obviously after each cycle the current is little increasing. So current remain continuous, but it doesn't mean that it will keep on increasing, because R is there, na? R is there in the load. So what I told you is, whenever the load contain R, I naught T will be periodic. It means it will increase to some extent, but then after increasing somewhat positive value, after maybe 4, 5, 10 cycles, it will keep on repeating again. It will not keep on increasing. It will not be like this that we have studied before, like this inductor situation. In this inductor it will keep on increasing because there was no R. But now you have R, now you have the resistance. Because you have the resistance, so it will, after maybe 4 or 5 cycle, it will repeat the current. I mean the current value will repeat, and it will not be like increasing in every cycle. No sir, it will not be like this. I hope it is clear. So whenever you have RL load, the conduction will be continuous. Conduction will be continuous. And periodic. I naught T will be continuous and periodic. Conduction will be continuous and periodic. Okay. So the conduction will be continuous and periodic. The next thing is, since the conduction is continuous and periodic, this current is periodic. So VLT average will again be 0. VLT average will be 0. Okay. It means whatever the output average is, that average must be equal to R only. Now can you calculate the output average value? This average value. What is the period of this wave? The period is 2 pi. You can see that this alpha point will repeat at 2 pi plus alpha. So the period is 2 pi radian. Okay. So what we can do is, we can calculate the average value of the output. Average value is 1 upon pi. Take the area. From alpha to pi, you have to take the area, because from pi to 2 pi plus alpha, area is 0. So from alpha to pi, the wave is Vm sin omega t, d omega t. Okay. You can calculate this area. This area came out to be Vm by pi. Integration of sine is minus cos, upper limit minus lower limit is 1 plus cos alpha. This is my output average voltage. And we know that whatever the output average voltage is, that must be equal to R into I naught T average. So from here you can calculate I naught T average value. So I naught T average value came out to be I naught T average came out to be V naught T average divided by R. Okay, that is equal to Vm by pi R into 1 plus cos alpha. Okay, easy peasy. Don't try to remember anything. Don't try to cram anything. Okay, try to understand everything. So I told you how the wave shape will look like. Now let's proceed with the next case. Now you have LE load. Now you have LE load and you have this thyristor. Now tell me guys, what will happen? First of all, let's assume that it is not conducting. Thyristor is not conducting at this point is 0. Okay. If thyristor is not conducting, then there is no current. Initially I am assuming that there is no current and no thyristor is conducting. If thyristor is not conducting, it means the current is 0. Whatever this voltage, let's say this E volt is there, E is there. So if this is E volt and this is ground, then this volt will also be E. Why? Because there is no drop in the inductor, there is no current, na? So there is no drop in the inductor. So this voltage will remain at E, output voltage will remain at E if there is no current in the load. If there is no current in the load, there is no drop across the inductor. So this E voltage will appear at the output. So the output voltage will be E only. The total output voltage will be E only. Okay, if there is no current. Now, to make this thyristor under forward blocking mode, this voltage has to be greater than E. This voltage has to be greater than E. It means VST has to be greater than E. Then only you can fire it. So VST is Vm sin omega t should be greater than E. So omega t should be greater than sine inverse of E by Vm. It means alpha has to be greater than this value. If alpha is greater than this value, then only you can fire the thyristor, because then only it will be under forward blocking mode, because this side has to be greater than E value. So if you are firing alpha is greater than this value, then only you can fire it. Once you fire it, it will become forward bias and it will start conducting. Okay, so now what you can do is, let's say we are firing at some angle alpha and this alpha is greater than this value. Okay, so alpha is greater than this value. So we are firing at angle alpha. Now what will happen, guys? Tell me. As soon as you fire this, it will be sorted. If it is sorted, then the output voltage will remain as supply voltage. And let me draw the E level also. Let's say this is my E level. This is E level. Okay, this is E. So you can see that supply voltage is equal to E at this instant. At this instant, you can say that this is my supply voltage. At this instant, E is equal to supply voltage, right? At this instant, E is equal to supply voltage. So this instant I call theta. Let's say this is theta. Theta is this. I mean, Vm sin omega t is equal to E, na? So alpha has to be greater than theta. Okay? How to calculate this theta? Vm sin omega t equal to E. You put it equal to E and calculate this omega t. Omega t is equal to sine inverse of E by Vm. This I call as theta. So alpha has to be greater than this theta. That's why alpha is greater than that. Okay. So I fire the thyristor at angle alpha. As soon as you fire it, what will happen, guys? As soon as you fire it, what will happen? The output voltage will be same as the supply voltage. Okay. So the output voltage will look like this. Output voltage will be same as the supply voltage. Now the question is, up to what instant the output voltage will be there? Is it up to pi? Let's say up to pi. Let's draw it up to pi. And draw the wave shape up to pi. But it doesn't mean that in every situation it will be up to pi. Okay, this is my alpha. This is pi. Okay. Now, this level is E. Let me draw the level E. E here also. This level is E. Why I am drawing E here in the output? Just to show you about the VLT. Just to show you the VLT. Whatever the output voltage is, that output voltage will be divided into two parts. Okay. I can say it like this. V naught T can be equal to VLT plus E. Is it fine, guys? V naught T can be equal to VLT plus E. Fine. It means VLT will be equal to VLT will be equal to V naught T minus E. V naught T minus E. It means if this yellow color is V naught T, then this E will be VLT. Now you can see that this difference will be VLT. Let me repeat this. If this yellow color is V naught T, then V naught T minus E will be VLT. So you can see that up to this instant, this VLT is positive. So the current has to rise. The current has to rise. Up to this instant, the current will rise. That's why I have plotted this E to check up to what instant VLT is positive. So current will start from 0 here and it will reach to the maximum value at this instant. Is it clear, guys? It will reach to this maximum up to at this instant. Okay, I hope it is clear. Now what will happen? After that, VLT is negative. You can see that. You can see that VLT is negative. This is negative voltage. VLT is negative because this E is greater than V naught T. If E is greater than V naught T, then VLT is negative. If VLT is negative, current will start decreasing. Current will start decreasing. So current will go down. Current will start decreasing. Current will go down, but at pi, you can see that current has not decreased to 0. At pi, up to pi, it will, because we have seen only up to pi now. At pi, current has not become 0. It means this inductor current is not 0 at pi. What will happen after pi? Tell me, guys. It means after pi, thyristor has to conduct. Why? Because there is no other alternative path for this current. So this inductor will make this thyristor conduct, because it will not let the thyristor off, because the current has developed and there is no alternative path. So after pi also, inductor will conduct, the thyristor will conduct. Okay, up to what instant? Let's call it beta. Let's call it beta instant. Okay, up to beta instant, current has to the thyristor has to conduct. At this instant beta, the current will become 0, because you can see that the inductor voltage is negative. This is the inductor voltage. This is negative. Okay, up to what instant the current thyristor will conduct? Up to the instant by which this current has become 0. So this current has become 0 at beta. So up to that instant, the thyristor has to conduct, and the output voltage up to that instant will be like this. This is my output voltage. I have shown you the output voltage. This yellow color is the output voltage. Now what will happen after that? After that, from this beta onward, from beta to again 2 pi plus alpha, there will be no current. There will be no current. If there is no current, then the output voltage will be at E. Output voltage will go at E level. Output voltage will remain at E. Is it fine? And then you are firing at 2 pi plus alpha. Then again you are firing at 2 pi plus alpha, and the output voltage will be like this. Is it fine, guys? This will be my output voltage wave shape. And you can see that during this interval alpha to pi, since the current is repeating the value, current will come to the same value. At alpha it was 0, at beta it is 0 again. So you can see that from alpha to beta, the VLT area of VLT dt, from alpha to beta, it will be 0. It will be 0. Why? Because the current is repeating. So whatever this positive area is, the same will be the negative area, because this white color wave shape is for VLT. This white color I have shown for VLT. So whatever this positive area, the same will be the negative area. Okay? You should know the inductor. Once you get the idea about the inductor, believe me, your understanding will be enhanced. Okay? So you should know the inductor analysis. You should know the behavior of the inductor. So using the behavior of the inductor, we can plot the wave shape. There is no problem at all. Now, what I want to do is, I want to increase the value of E. Now, if you further increase the value of E, then it might be possible that the current becomes 0 before pi or at pi. It might be possible that the current becomes 0 at pi or before pi. Now you'll ask me, sir, how? Okay, let's take that case also. Let's take that case also. So what I have is, I have this circuit, LE circuit is there, and wait a minute. I have this LE circuit. Here you have the thyristor, and you have L, and you have E. This is the circuit. Now if I increase the value of E, if I increase the value of E, this is my supply voltage. This is my supply voltage, okay, and here you have omega t. This is 0, this is pi, this is 2 pi. What you have done is, let's say you have increased the value of E up to this level. You have increased the value of E up to this level. I mean, E is high enough. You have increased the value of E. E is high enough. So obviously you can fire after this theta, because this point will be theta. So alpha, let's take alpha is this. This is my alpha. So at this instant I fired the thyristor. If you have fired the thyristor, then output voltage will be same as the supply voltage. Tell me. So if I want to draw the output voltage, then at alpha the output voltage will be same as the supply voltage, VST. Output voltage will be same as the supply voltage. It means the output voltage will start at this point. At this point the output voltage is this, and it will be same as the supply voltage. So the supply voltage is changing like this, so it will also change like this. Now let's draw the E level also. No? Let's draw the E level also. This is my E level. Okay, this is my E level. Now the output voltage, let's draw the output voltage again. So output voltage will go like this, and it will not reach up to pi, I suppose. First let's draw the output voltage completely, and then we'll see whether it will conduct up to pi or not. Okay, whether it will conduct up to pi or not. So at alpha we have fired it, so the output voltage will be same as the supply voltage, and it will be like this. Wait a minute, it is creating problem. Okay, let me draw it again. This is my pi instant. So the output voltage will be like this. It will go like this, and let's draw it like this. Okay, now it might be possible that this positive area, this is VLT, become equal to the negative area before this pi. Let's say at this instant beta, before the pi, this positive area become equal to the negative area. What does it mean? It means the current will be from alpha to beta only. This is pi and this is beta. This point is beta, this point is pi. So current will go and it will reach to the maximum at this point, and then it will go 0 here. So it might be possible that the current becomes 0 before pi. Be careful, guys. It might be possible that the current becomes 0 before pi. Remember this point. I hope it is clear. Okay. So the current will be discontinuous. We have seen that the current will be discontinuous. Now can you tell me, if the current is discontinuous, what will be the VLT average? What will be the VLT average? Tell me, guys, what is VLT average? If the current is discontinuous, it will be periodic. I told you, if the current is discontinuous, it will be periodic. If the current is periodic, what does it mean? It means the VLT average is 0. VLT average is 0. So now tell me, if VLT average is 0, take the average on both sides. So V0T average must be equal to, what is this V0T average? That will be equal to VLT average plus E. Is it fine? V0T average equal to VLT average plus E. We know that. VLT average is 0. So V0T average must be equal to E. Is it fine? Now from this relation you can say that V0T average has to be equal to E. Okay, V0T average has to be equal to E. The output voltage average has to be equal to E, because the current is discontinuous. Since the current is discontinuous, what you can say is, if the current is discontinuous, it will be periodic. If it is periodic, then the VLT average has to be 0. It means whatever the total output voltage average is, that must equal to E. Is it fine? So now you can say like this. I hope it is clear. Now let's come to the next topic. Next topic is this. You can analyze it yourself. Okay, do it yourself. Okay. Now again we have to look at the effect of the source inductance. But this time we have thyristor here. Now tell me, if you have the thyristor here, what will happen? Tell me, is it visible? Okay. Thank you. So now let's come to this circuit. In this circuit, we have Thyristor now. Okay. Now how to analyze this circuit? Again, what we need to do is first take Ls equal to 0. First take Ls equal to 0 and try to analyze this circuit and try to calculate the output voltage. And then we will take the Ls. And the firing angle for this Thyristor is alpha. So let's first take Ls equal to 0. If I take Ls equal to 0, then the circuit will look like this. You have the Thyristor here and you have the diode here. And you have a current source. Okay, you have the current source I0. Is it fine? And there you have the source VST. VST is Vm sin omega t. Fine. Now, what I need to do is I need to analyze this circuit. I need to look at the output voltage V0 t when there is no Ls. Ls is 0. Ls is 0. Now let's analyze it. First, what we are going to do is we are going to plot the wave shape. This is my supply voltage, omega t. This is 0, this is pi, this is 2 pi, okay? And the peak value, let's take this peak value as Vm. Okay. Now what I want to do is I want to plot two wave shape. One is V0 t and one is IST. One is IST. I want to plot these two waves. One is V0 t and one is IST. And I am firing at an angle alpha. I'm firing at an angle alpha. Now, if you are firing at an angle alpha, what will happen, guys? Before alpha, the current was freewheeling. Before alpha, the current was freewheeling. Okay? So, the output voltage remains 0. Before alpha, the output voltage will remain 0. Now, at alpha, you have fired this Thyristor. As soon as you fired this Thyristor, the entire current will flow through the source. And the output voltage, since the supply is connected in parallel with the output, so you can say that the output voltage will be same as the supply voltage up to pi. Output voltage will be same as the supply voltage up to pi, and the current, the supply current will be like this. This will be my supply current. Now at pi, what will happen? At pi, again freewheeling diode will start conducting, because output voltage cannot be negative. If there is a freewheeling diode, output voltage can never be negative. So what will happen at pi? At pi, this diode will conduct, freewheeling diode will conduct, and the output voltage will become 0 up to 2 pi plus alpha. Up to 2 pi plus alpha, you can say that the output voltage will become 0. Okay, and the freewheeling diode is conducting. Now at 2 pi plus alpha, again you have fired the Thyristor T1, so the output voltage will be again like this, 2 pi to 3 pi, and the current, the supply current will be like this. Is it fine? From 2 pi plus alpha to 3 pi. This will be my supply current, okay, and the current value is I0. From alpha to pi, it will be I0, and then from 2 pi plus alpha to 3 pi, it will be again I0. Is it clear, guys? Is it clear? This way we can plot with Ls equal to 0. If there is no source inductance, then you can plot it like this. Now you take the source inductance. Now I take the source inductance. So let's take the effect of the source inductance. What is the average voltage? The average voltage will be equal to V0 t average will be equal to, the period is 2 pi, you can see that. So 1 over 2 pi integration from alpha to pi Vm sin omega t d omega t. Now you can calculate the average value. It will be Vm by 2 pi. Now what is the integration of sign? Integration of sign is minus cos. Upper limit minus lower limit is 1 plus cos alpha. This will be my average output voltage if there is no source inductance. If Ls is 0, then this will be my average output voltage. Now let's take the effect of the source inductance. Now I am taking ls here. Okay, you take the ls. Okay, and the circuit is like this. Now the circuit is like this. This is my I naught. Okay, this is the circuit I have. And here I have the source voltage VST. Now let's see what will happen. Again, I have to plot the supply voltage. So this is the supply voltage I have. Okay, this is my Vm, this is minus Vm, and at alpha you are firing. I need to plot two more waves. One is the source current IST, and one is the output voltage V naught T. Let's try to plot these waves. Now we know that before alpha, the entire current was freewheeling. Before alpha, the entire current was freewheeling. So there was no current through the source. There was no current through the source. So the source current was 0 up to alpha. And the output voltage was 0 because the freewheeling diode was conducting. So the output voltage was 0. Output voltage was 0. Now, what will happen, guys? At alpha, you have fired this thyristor. As soon as you have fired this thyristor, what will happen, guys? As soon as you fire this thyristor, what will happen? Now, the current will not abruptly increase. In the previous case, the current abruptly increased. Okay? But now the current will not abruptly increase. What will happen? The current will increase to I naught, but it will take some time. Let's call it mu time. Let's call it mu time. During this interval, overlapping interval, this current will slowly increase, this current will slowly decrease. And the output voltage remains 0 because the freewheeling diode is still conducting. So you can say that from alpha to alpha plus mu, you can see that the output voltage will remain at 0. Output voltage will remain at 0 and the IST will increase to I naught. IST will increase to I naught. It will not be abrupt change. It will not be abrupt change like this. So it will take some time, alpha plus mu. And then it will remain I naught T. After this, it will remain I naught T. It will remain I naught T and the output voltage will remain at supply voltage. Output voltage will remain at supply voltage, okay? And at pi, what will happen? Pi again, the freewheeling diode will turn on. If freewheeling diode will turn on, then this will decrease. This will decrease to 0 again. Slowly it will decrease. And the freewheeling diode current will increase. And then at this instant, let's call it pi plus mu 2. At this instant, entire current is shifted to the freewheeling diode. Is it fine? And the output voltage will remain 0 because the freewheeling diode is conducting. From pi to pi plus mu 2, freewheeling diode is conducting. So output voltage will remain 0. Now what will happen after that? After that again, freewheeling diode will keep conducting. And this thyristor will remain reverse biased. Okay. Now again, it will conduct at 2 pi plus alpha. At 2 pi plus alpha, up to 2 pi plus alpha, freewheeling diode will conduct. Okay. Up to this instant, freewheeling diode will conduct and the supply current will be 0 and the output voltage will also be 0. Now at 2 pi plus alpha, again you have fired the thyristor T. Once you fire the thyristor T, again the current will rise like this. Current will rise like this and the output voltage will remain 0 up to the overlapping interval. Is it clear, guys? So you can see that the average output voltage will get reduced because in the previous case it was starting from alpha to pi. Now it is alpha plus mu to pi. And there is one more point. This overlapping interval at angle alpha, the overlapping start. This overlapping interval and this overlapping interval which start at pi. Because at pi again overlapping will be there now, because at pi this current has to increase, this current has to decrease. So there again two devices are conducting. So there will be overlapping again. So this overlapping angle mu 2 and this overlapping angle mu, they will be different. They will not be the same. Okay. Remember this point. So I told you how the wave shape will look like. Now the question is, what is this mu? Because we are not interested in this mu 2. Because during this mu 2, average is 0. So that's why we are not interested. We are interested only in this. Because in the previous case also, from after pi this was 0, here also after pi it is 0. So that's why we are not interested in calculation of the mu 2. Okay. we are interested in calculation of this mu interval, the starting mu interval, okay? And what will be the average output voltage? How to calculate that? It's very simple. During the overlapping interval, the circuit will look like this. This will be sorted and this diode will also be sorted, okay? And here you have the current source. Here you have the current source. Is it fine, guys? This current source is of I naught value and this source is a sinusoidal source, Vm sin omega t. Vm sin omega t, and this is my Ls. Now what will happen is, now tell me guys, what will happen is, during the overlapping period, this current, there is two current, one is this current and one is this current. So you can see that the net current in this diode is I naught minus I mu. This is I mu current. So you can see that this diode current will decrease and this current will increase. So tell me, during the overlapping interval, this current will increase to 0 to I naught, because this I mu is same as the supply current. I mu is same as the supply current. So I can write the KVL equation as Vm sin omega t is equal to Ls d I mu by dt. I have written the KVL. I have written the KVL in this loop as we did previously. Okay, so you can take it like you can take this dt on this side. So Vm sin omega t into dt divided by Ls is equal to d I mu. Is it clear, guys? Tell me. Vm sin omega t divided by Ls into dt is equal to d I mu. Now what we can do is we can divide it with omega, multiply with omega. So this dt will become d omega t. This dt will become d omega t. And we can integrate on both sides. But let me tell you, the I mu changes from 0 to I naught and this omega t changes from alpha to alpha plus mu this time. In case of diode, it was from 0 to mu. But now, since the conduction starts from alpha, so the overlapping will be from alpha to alpha plus mu. So it will be Vm by omega Ls, and you solve, you take the integration of sine. Sine integration is minus cos. So upper limit minus lower limit, you will get cos alpha minus cos of alpha plus mu, okay, is equal to I naught. From here you can calculate the mu value. Here you can calculate the overlapping value, okay, the mu value. Once you get this mu value, now you can calculate the average output voltage. So the average output voltage will be V naught T average will be equal to 1 upon 2 pi, the period is 2 pi. Now the area should be from alpha plus mu to pi. Alpha plus mu to pi, and here you have to write Vm sin omega t. Is it clear, guys? Okay, now take this Vm out. So Vm upon 2 pi, and the integration of sine is minus cos, upper limit minus lower limit, 1 plus cos of alpha plus mu. Okay, you will get this. This is my V naught T average. Once you get this mu, you can also calculate this average value. Okay, and you can also check if mu is 0, if let's say Ls is 0, then mu will become 0, and then it will become Vm by 2 pi 1 plus cos alpha, which is the previous case. It means it is correct, the expression is correct. Okay, so I have calculated this expression, I have derived this expression, you can check it, and I hope you got the point. So it is again similar to the previous situation. I hope it is clear. Now we are going to start with the single phase full wave rectifier, okay, controlled rectifier. From this point onward, I think we should continue in the next class, because I want to stop it here. Okay, guys, so let's stop it here, and from this point onward we will continue in the next class. So in the next class I will continue from this point onward, and first I will revise you these controlled rectifier, every controlled rectifier in the first 1 or maybe 1.5 hour, and then we'll take this 3-phase control rectifier, and then we will go to the DC-DC converter. Okay, we'll go to the DC-DC converter, and then we'll revise a little bit of inverter. Or what we can do is, if you want me to revise the DC-DC converter and inverter, I can revise that. Please comment about that. Please tell me what topic you want me to revise you. Tell me, is it DC-DC converter or inverter, or you want to continue this part only, or you want to continue the Thyristor part only? Tell me, guys, which topic you want me to revise. Tell me, everyone, which topic you want me to revise. Is it DC-DC converter or inverter or you want to continue from this topic onward? The full wave controlled rectification. Tell me guys, which topic you want? DC-DC converter and today's part. Okay, Raghuram. Okay, anyone else? Tell me guys. Anyone else who want me to, if you want me to continue from this topic onward, I'll continue from this topic onward. Okay, this topic. Okay, Ashok is saying inverter. Okay, so what I will do is I will devote 1 hour on DC-DC converter, because DC-DC converter is very simple. So only 1 hour I will devote on DC-DC converter, and you will understand from that 1 hour. And 1 hour on this topic. On this topic, I'll devote 1 hour. So approximately you can say 2 hours will be 2 or maybe 2.5 hours will be devoted. Then last 1 hour I'll devote on inverter. Okay, because inverter is not that difficult and that much long. So last 1 hour I'll devote on inverters. Okay, guys. So that's all for today's session, guys. And see you in the next class. Next class will be on tomorrow. So we'll continue the next class on tomorrow. Thank you and take care. Bye.